Have you ever wondered what secrets lie beyond our sight? What if the universe is full of mysteries waiting to be uncovered? How did it all begin, and what lies beyond? Join us as we uncover the most perplexing mysteries of the universe, from the birth of stars to the search for alien life. About 14 billion years ago, the universe as we know it began with an event known as the Big Bang. This wasn't an explosion in the traditional sense, but rather a rapid expansion from a singular point of almost infinite density and temperature. In the first fractions of a second, the universe expanded exponentially and cooled dramatically. During these critical moments, elementary particles such as quarks and gluons emerged, which eventually combined to form protons and neutrons. These particles are the building blocks of atoms, the fundamental units of matter that make up everything in the universe. Several 100,000 years later, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This period is often referred to as the recombination epoch. This relatively tranquil period allowed the cosmic microwave background radiation to propagate, which we can still observe today with sensitive telescopes. Over billions of years, gravity pulled matter together to form stars, galaxies, and eventually the complex structures we see in the cosmos. Though scientists have developed sophisticated models to describe these processes, the exact mechanisms and conditions of the very first moments after the Big Bang remain a tantalizing mystery, continuously driving inquiry and discovery in the field of cosmology. Speaking of exploring the cosmos, have you ever wanted to command your own starship and journey through the galaxy? I'm thrilled to introduce you to Star Trek Fleet Command, an epic 4X MMO game that lets you dive deep into the massive Star Trek universe.
Hey, Commander. Your treasury is full. Complete your daily goals and defeat enemies to earn points and unlock new rewards.
In Star Trek Fleet Command, you can recruit legendary characters from over 50 years of Star Trek stories. Imagine commanding iconic ships like the USS Enterprise, engaging in epic battles, negotiating alliances, and expanding your territory. And there's something new on the horizon. The latest update takes you into the Mirror universe. You can now recruit epic officers like Mirror Picard, a master strategist, and Mirror Borg Data, a force of technological superiority. And don't miss out on the 7 days login reward. Log in every day to receive daily welcome gifts and unlock the epic Romulan officer Nero after 7 days of playing. I've been playing this game, and I must say, it's incredibly strategic and engaging. The thrill of exploring the galaxy, the stunning graphics, and the continuous updates make it a must-play. Plus, it's free to play on both desktop and mobile, allowing you to switch between devices seamlessly. Just scan this QR code or click the link in the description to download Star Trek Fleet Command for free. And, as a special bonus for new players, use the promo code BOOST to get a beginner station upgrade content pack with 300 Latinum, 100k Pastille, and 10k Tritanium. Join millions of players around the world, form alliances, conquer territories, and dive into the ever-expanding Star Trek universe to become the greatest commander in the galaxy. So what are you waiting for? Click the link, download the game, and boldly go where no one has gone before. To measure the age of the universe, scientists employ several meticulous methods, one of which involves studying the cosmic microwave background radiation. The CMB is essentially the afterglow of the Big Bang, a faint radiation that permeates the entire universe. By examining the temperature fluctuations and density variations in the CMB, scientists can estimate the time elapsed since the universe began to cool after its rapid initial expansion. This analysis has led to the understanding that the universe is approximately 13.8 billion years old. Another critical method involves the observation of distant celestial objects, particularly Type Ia supernovae. These stellar explosions serve as standard candles because they have a known intrinsic brightness. By measuring how bright these explosions appear from Earth, astronomers can determine their distance from us. Combined with the measurement of the expansion rate of the universe, known as the Hubble constant, these distances help calculate how long it has taken the universe to reach its current size. This approach corroborates findings from the CMB, strengthening the estimate that the universe is around 13.8 billion years old. These methods, along with others like studying the oldest star clusters and galaxy dynamics, provide a multifaceted approach that enriches our understanding of the universe's age. While the Big Bang theory remains the most widely accepted explanation for the origin of the universe, several tantalizing mysteries still surround it. While the Big Bang theory remains the most widely accepted explanation for the origin of the universe, several tantalizing mysteries still surround it. One of the foremost enigmas involves the nature of dark matter and dark energy. These elusive components are thought to make up roughly 95% of the universe's total mass and energy, yet they remain undetected by conventional means. Dark matter is inferred from its gravitational effects on visible matter, like galaxies and galaxy clusters, but its exact composition remains unknown. Dark energy, which is believed to drive the accelerated expansion of the universe, is even more mysterious. Understanding these components is critical for a complete picture of the universe's birth and evolution. Another perplexing issue is the question of what existed before the Big Bang. The traditional Big Bang model describes the universe's evolution from an incredibly dense and hot state, but offers no insight into the conditions preceding this event. Several hypotheses have been proposed, such as the idea of a cyclic universe that undergoes endless cycles of expansion and contraction, or the concept of a multiverse where our universe is just one of many. These ideas, while intriguing, remain speculative and largely beyond the reach of current observational capabilities. Furthermore, scientists are still grappling with the reconciliation of general relativity, which governs the cosmos at large scales, with quantum mechanics, which describes the subatomic realm. Bridging these two pillars of modern physics could potentially unlock new insights into the earliest moments of the universe and address some of the deepest mysteries of the Big Bang. Despite remarkable advancements in cosmology, several profound unknowns persist in our understanding of the universe's structure. One of the most glaring gaps in our knowledge is the nature and role of dark matter. While it is estimated to account for approximately 27% of the universe's mass-energy content and is essential for the formation of cosmic structures such as galaxies and clusters, dark matter has yet to be directly detected. Its exact properties and how it fits into the standard model of particle physics remain elusive, leaving scientists to infer its presence through gravitational effects on visible matter and cosmic radiation. Equally mystifying is the phenomenon of dark energy, which constitutes roughly 68% of the universe's mass energy budget. Discovered through the observation that the universe's expansion rate is accelerating, dark energy's true nature is one of the biggest enigmas in modern cosmology. It is often described as a property of space itself, perhaps linked to the cosmological constant proposed by Einstein, but this interpretation remains purely theoretical. Understanding dark energy is crucial because it affects the future evolution and ultimate fate of the universe, determining whether it will expand forever, collapse back on itself, or reach a stable size. Another significant challenge lies in the seemingly anomalous behavior of certain cosmic structures. Observations have indicated that there may be deviations from established models, such as discrepancies in the Hubble constant derived from different measurement methods. This Hubble tension problem suggests that there could be unknown factors influencing cosmic expansion, potentially hinting at new physics beyond our current understanding. These unknowns collectively highlight not only the depth of mystery surrounding the universe's structure, but also the exciting potential for groundbreaking discoveries in cosmology. Scientists employ a variety of sophisticated techniques and instruments to uncover the secrets of the universe. Central to their toolkit are telescopes that operate across the electromagnetic spectrum, from radio waves to gamma rays. Space-based observatories like the Hubble Space Telescope and the James Webb Space Telescope offer unprecedented views into distant galaxies, star-forming regions, and even potential exoplanets. Ground-based telescopes, such as those part of the Very Large Array or the Atacama Large Millimeter Sub-Millimeter Array, provide high-resolution images and spectra that reveal the composition, motion, and other properties of celestial objects. These observations allow scientists to test theories, refine models, and gain insights into phenomena such as black hole formation, galaxy evolution, and cosmic inflation. In addition to telescopes, particle accelerators like the Large Hadron Collider, LHC, enable scientists to recreate conditions similar to those just after the Big Bang. By smashing particles together at near-light speeds, researchers investigate fundamental forces and particles that make up the universe, seeking to understand their behavior and interactions. This research is pivotal in exploring dark matter, dark energy, and other unknown aspects of the universe's makeup. Scientists also utilize gravitational wave detectors such as LIGO and Virgo, which have opened a new window to the cosmos by detecting ripples in space-time caused by cataclysmic events like black hole mergers or neutron-star collisions. Moreover, advancements in computational science play a crucial role. Powerful supercomputers run simulations of cosmic phenomena, from the dynamics of galaxy clusters to the evolution of large-scale structures in the universe. These simulations are vital for interpreting observational data, testing theoretical models, and predicting new phenomena. By integrating data from diverse sources and using multifaceted approaches, scientists continuously refine our understanding, tackling enduring mysteries and pushing the boundaries of what we know about the universe. Galaxies, those magnificent cosmic assemblies of stars, gas, dust, and dark matter, hold many mysteries that continue to intrigue astronomers and cosmologists. One of the most enduring enigmas is the role and nature of supermassive black holes, which reside at the centers of most galaxies, including our Milky Way. These black holes, with masses ranging from millions to billions of times that of our Sun, influence the dynamics and evolution of their host galaxies. Yet, how they form and grow remains a subject of intense study. For instance, it is unclear whether galaxies formed around pre-existing black holes, or if black holes grew by accumulating matter from their galaxies. Another profound mystery within galaxies is the distribution and behavior of dark matter. While dark matter does not emit light and is invisible to traditional telescopes, its presence is inferred from its gravitational effects on visible matter. In galaxies, dark matter forms a halo around the visible components and plays a crucial role in holding galaxies together and governing their rotational speeds. Scientists are striving to detect dark matter directly and understand its properties, but so far it remains one of the most elusive elements of the universe. Additionally, the process of galaxy formation and evolution itself is riddled with questions. How do galaxies merge? How do new stars form in different types of galaxies? And what causes galaxies to cease star formation? Furthermore, the phenomenon of galactic feedback, whereby energetic processes such as supernovae or active galactic nuclei influence their surroundings, presents another layer of complexity. This feedback can drive powerful winds that expel gas from galaxies, affecting star formation and the intergalactic medium. Unraveling these interactions is vital for comprehending both the small-scale and large-scale structure of the universe. By probing these and other galactic mysteries, scientists aim to piece together the broader puzzle of how the universe evolves from the cosmic web of matter and energy into the multitude of galaxies we observe today. Galaxies form from fluctuations in the density of matter in the early universe, a process that began shortly after the Big Bang. Initially, slight variations in the density of the primordial gas, which was predominantly hydrogen and helium, grew over time due to gravitational attraction. Regions with slightly higher densities pulled in more matter, becoming denser and eventually collapsing to form dark matter halos. These halos served as gravitational wells, drawing in gas that cooled and condensed to form the first stars and star clusters, eventually leading to the formation of protogalaxies. As these protogalaxies evolved, they grew by accreting more matter and merging with other protogalaxies. Collisions and mergers played a vital role in shaping the structure and morphology of galaxies. For instance, when two spiral galaxies merge, they can potentially form an elliptical galaxy depending on the dynamics and angles involved in the collision. Elliptical galaxies tend to have older star populations and less gas and dust compared to their spiral counterparts, which often have well-defined disk and spiral structures rich in star-forming regions. The variety of galaxy shapes, spiral, elliptical, and irregular, further arises from differences in their formation and interaction histories. Spiral galaxies, like our own Milky Way, typically form in regions with ample rotational momentum, which causes the gas and stars to flatten into a rotating disk with distinctive spiral arms. These arms are sites of active star formation, fueled by the interstellar gas and dust. Elliptical galaxies, on the other hand, appear more spherical or ellipsoidal and result from more violent mergers that randomize star orbits, leading to an overall older and structurally smoother appearance. Irregular galaxies do not fit neatly into either category and often attain their non-standard shapes due to gravitational interactions or distortions caused by nearby galaxies. Thus, while the initial conditions of the primordial universe set the stage, the dynamic processes of gravitational collapse, rotational motion, and galactic collisions and mergers over billions of years give rise to the diverse and captivating array of galaxy shapes observed today. Researchers continue to study these processes using advanced simulations and observations, seeking to refine our understanding of galaxy formation and evolution. The Milky Way galaxy is a remarkable and complex structure that holds many unique features, making it a subject of endless fascination for scientists. One key attribute is its distinctive spiral structure, characterized by prominent arms that extend outward from a central bulge. These spiral arms are sites of active star formation, populated by young, bright stars, nebulae, and interstellar gas and dust. The center of the Milky Way, known as the galactic center, houses a supermassive black hole named Sagittarius A*, which has a mass around 4 million times that of our Sun. This black hole exerts a significant influence on the dynamics of stars and other matter in the central region. Another unique aspect of the Milky Way is its extensive halo, which extends far beyond the visible disk and contains old stars, globular clusters, and a substantial amount of dark matter. This halo plays a crucial role in the gravitational stability of the galaxy and influences the motion of stars in its periphery. Moreover, the Milky Way is part of a larger cosmic structure known as the Local Group, which includes more than 50 other galaxies, such as the Andromeda Galaxy and the Triangulum Galaxy. These neighboring galaxies gravitationally interact with the Milky Way, leading to intriguing phenomena such as tidal streams of stars and gas pulled from smaller satellite galaxies. The Milky Way also exhibits a relatively flat rotation curve, where the orbital velocity of stars and gas remains constant at large distances from the center, rather than decreasing as would be expected from the visible mass alone. This observation provides compelling evidence for the presence of dark matter, making our galaxy a key site for studying the effects of this mysterious substance. Furthermore, the Milky Way's position within the universe offers a unique vantage point for astronomers. As inhabitants of this galaxy, we have the opportunity to observe and study its structure, history, and dynamics in great detail, offering invaluable insights into the processes governing galaxy formation and evolution. Spiral galaxies, like our Milky Way, have a number of peculiar features that make them particularly intriguing and visually stunning objects in the cosmos. One of their most defining characteristics is their well-defined spiral arms, which spiral outwards from a central bulge or nucleus. These arms are not static structures, they are actually density waves, regions of higher density that move through the galaxy. As gas and dust pass through these waves, they get compressed, leading to the formation of new stars. Consequently, spiral arms are rich with young, hot stars, glowing brightly in shades of blue and white, as well as numerous star-forming regions laden with gas and dust. Another peculiar aspect of spiral galaxies is their rotational dynamics. The stars within the disk of a spiral galaxy generally follow nearly circular orbits around the galactic center. Unlike the solar system, where planets farther from the sun orbit more slowly, the stars in a spiral galaxy tend to rotate at relatively constant speeds, regardless of their distance from the center. This phenomenon results in the flat rotation curves observed in spiral galaxies. This unexpected consistency in rotational velocity is one of the primary pieces of evidence for the existence of dark matter, a mysterious and invisible substance that appears to make up a significant portion of a spiral galaxy's mass and provides the necessary gravitational pull to maintain these high orbital speeds. Spiral galaxies also often contain a feature known as a galactic bar, a linear structure of stars that extends from the central bulge and can influence the dynamics of the entire galaxy. The presence of a bar suggests complex gravitational interactions and can impact the distribution of stars, gas, and dust within the galaxy, possibly playing a role in funneling material towards the core and triggering bursts of star formation or even feeding central supermassive black holes. Finally, the evolution and morphology of spiral galaxies are influenced by their interactions with other galaxies. Spiral galaxies can exhibit features such as tidal tails, bridges, and rings as a result of gravitational interactions, collisions, or mergers with other galaxies. These interactions can dramatically alter their structure, driving both star formation and the redistribution of gas and stars within the spiral arms. Each peculiar feature of spiral galaxies not only defines their stunning appearance, but also offers deep insights into the underlying physical processes that govern their formation and evolution. Elliptical galaxies, though often considered more straightforward in structure compared to their spiral counterparts, harbor several unexplained phenomena that challenge and intrigue astronomers. One major mystery involves the formation and evolution of these galaxies. Elliptical galaxies are typically composed of older, redder stars and exhibit little ongoing star formation, with most of their interstellar medium having been expended or expelled. The traditional model posits that elliptical galaxies form primarily through the merger of smaller galaxies. However, observations of some massive elliptical galaxies forming rapidly in the early universe, within just a few billion years after the Big Bang, complicate this picture. These observations suggest the existence of other, possibly more rapid and efficient formation mechanisms. Another enigmatic feature of elliptical galaxies is their central regions, which often host supermassive black holes. It's well established that there is a correlation between the mass of the central black hole and the velocity dispersion of the stars in the galaxy's bulge, known as the M-sigma relation. However, the exact nature of this relationship and the processes that lead to such close coupling remains poorly understood. Furthermore, the prediction and observation of supermassive black holes are often complicated by the lack of significant accretion activity in many elliptical galaxies, making these black holes difficult to detect. Elliptical galaxies also exhibit a puzzling variety of kinematic properties. While some show rotation similar to spiral galaxies, many possess complex velocity patterns and kinematic misalignments, where the rotation axis of the stars is not aligned with the light distribution axis. These features suggest a tumultuous evolutionary history, likely involving multiple merger events that scrambled the stars' orbits. Additionally, the distribution and behavior of dark matter in elliptical galaxies is not as well constrained as in spirals. The dynamics and gravitational influences observed in elliptical galaxies sometimes do not align neatly with predictions, hinting at missing components or misunderstood physics. Finally, some elliptical galaxies possess faint, extended halos or diffuse light known as intracluster light, originating from stars that have been stripped from galaxies during interactions and mergers within galaxy clusters. The exact mechanisms behind the formation and distribution of these stars remain an area of active research. Each of these unexplained phenomena in elliptical galaxies not only highlights the complexities of these seemingly simple structures, but also emphasizes the necessity for continued observations and theoretical advancements in our understanding of galactic formation and evolution. The irregular shapes of some galaxies, often classified simply as irregular galaxies, are primarily the result of gravitational interactions and mergers with other galaxies, as well as intrinsic factors like star formation processes and supernova explosions. Unlike the well-defined structures of spiral or elliptical galaxies, irregular galaxies often display chaotic forms with no discernible symmetry or standard organization. One of the most common causes of irregular shapes is galactic collisions and interactions. When galaxies pass close to one another or collide, the immense gravitational forces can distort their structures, pulling stars, gas, and dust into irregular shapes. These interactions can result in tidal forces that stretch and warp the original structure of the galaxies, creating features such as tidal tails, bridges of matter between galaxies, and irregular, clumpy distributions of stars. Sometimes, these interactions can also strip gas from galaxies, fueling bursts of star formation that contribute further to the galaxy's irregular appearance. Another factor contributing to the irregularity is the process of rapid and intense star formation, often triggered by galactic interactions or other dynamic processes. High rates of star formation can lead to the creation of numerous stellar clusters and diverse star-forming regions scattered throughout the galaxy, lacking the orderly organization seen in spiral arms. Additionally, the impact of supernova explosions, which are the catastrophic deaths of massive stars, can inject energy into the surrounding interstellar medium. This energy can blow bubbles in the gas, generate shock waves, and distribute material erratically, all contributing to an irregular morphology. Intrinsic factors also play a role. Some irregular galaxies may simply be in a transition phase, having not yet settled into a more stable structure like a spiral or elliptical galaxy, due to ongoing processes such as accretion of matter, internal instabilities, or relatively low gravitational binding compared to more massive galaxies. Irregular galaxies' varied and often chaotic appearances are therefore the result of a combination of external forces, such as gravitational interactions and mergers, and internal dynamic processes that govern star formation and gas distribution. These galaxies serve as a testament to the dynamic and ever-changing nature of the universe, offering valuable insights into the processes of galaxy evolution and the transformative power of gravitational interactions. The impending collision between the Andromeda Galaxy and our Milky Way galaxy presents a multitude of unknowns that intrigue astronomers and cosmologists. One of the primary uncertainties is the precise timeline of this colossal event. Estimates suggest that the closest approach will occur roughly 4 to 5 billion years from now, but the exact timing and sequence of events leading up to the merger depend on numerous factors, including the galaxy's current velocities, angles of approach, and the distribution of mass within each galaxy. Another significant unknown lies in predicting the precise outcomes of the collision. While models and simulations provide some insights, the complexity of the interactions makes definitive predictions challenging. For instance, it remains uncertain how the stars, gas, and dark matter in both galaxies will redistribute during the merger. Although individual stars are unlikely to collide due to vast interstellar distances, the gravitational forces will dramatically reshape the galaxies. It's predicted that the collision will likely result in the formation of an elliptical galaxy, sometimes referred to as Milkomeda or Milkdromeda. However, the detailed structure and properties of this resultant galaxy are still speculative. The fate of our solar system is also an open question. During the collision, our solar system could be flung to a different location, possibly further out in the remnant galaxy, or it might be drawn closer to the galactic core. The gravitational dynamics of the merger will induce significant perturbations in the orbits of stars, potentially altering the solar system's position over millions of years. Another related question is how star formation rates might change. The collision is expected to trigger intense star formation as interstellar gas clouds collide and compress, but the scale and duration of this starburst phase are uncertain. Additionally, scientists are keen to understand the role that the supermassive black holes at the centers of both galaxies, namely Sagittarius A* in the Milky Way and the black hole in Andromeda, will play in the merger. These black holes are expected to eventually coalesce, creating powerful gravitational waves detectable across the cosmos. The exact process and timeline of this black hole merger, along with its implications for the surrounding regions of the galaxy, are still areas of active research. These unknowns highlight the fascinating and dynamic nature of galactic evolution, prompting ongoing studies and simulations aimed at refining our understanding of the future collision between Andromeda and the Milky Way. This impending cosmic event offers a unique opportunity to observe and study the complex interactions that shape galaxies over billions of years. Galactic evolution, the process by which galaxies form and transform over cosmic time, is riddled with intriguing mysteries that continue to captivate scientists. One significant enigma involves understanding the detailed mechanisms behind galaxy formation shortly after the Big Bang. While the LCDM model, lambda cold dark matter, offers a broad framework for explaining how small fluctuations in the density of the early universe grew into the vast cosmic structures we see today, the precise pathways leading to the formation of the first galaxies remain elusive. Observations of early galaxies, some forming as early as a few 100 million years after the Big Bang, suggest that these objects evolved more quickly and more complexly than our current models can fully explain. The role of supermassive black holes in galactic evolution is another area fraught with unknowns. These massive entities, found at the centers of most large galaxies, seem to play a crucial role in regulating galaxy growth. However, the exact relationship between a galaxy's central black hole and its evolution is not well understood. This relationship is exemplified by the M-sigma relation, which correlates the mass of the black hole with the velocity dispersion of the stars in the galaxy's bulge. How these black holes grow to such enormous sizes and how they impact the formation and behavior of the surrounding galaxy remains a matter of active research. Do they regulate star formation through feedback processes such as outflows and jets? Or do they merely grow alongside the galaxy without directly influencing its evolutionary path? Dark matter also adds a layer of complexity to our understanding of galactic evolution. While it is clear that dark matter halos provide the gravitational scaffold necessary for galaxy formation, the nature of dark matter itself is still unknown. Understanding how dark matter interacts with ordinary matter and how it influences processes such as galaxy clustering and the formation of cosmic filaments is essential for a comprehensive picture of galactic evolution. Additionally, the distribution and behavior of dark matter within galaxies, especially dwarf galaxies which are dark matter dominated, pose significant challenges and questions for cosmologists. Galactic mergers and interactions, common processes that profoundly shape galaxies, introduce further mysteries. While it is known that such interactions can trigger intense bursts of star formation, as well as significant morphological transformations from spirals to ellipticals, the exact outcomes of these events depend on numerous variables, including the mass ratios of the interacting galaxies, their relative velocities, and angles of approach. Simulations offer some insights, but the sheer complexity of these processes means that many details about how galaxies evolve through interactions remain unclear. Lastly, the impact of environmental factors such as a galaxy's location within a cluster or its interactions with the intergalactic medium adds another layer of uncertainty. Galaxies in dense cluster environments can undergo processes like ram pressure stripping, where their gas is stripped away by the intra-cluster medium, quenching star formation. How these environmental processes collectively shape galaxy evolution and diversity across different environments is a significant ongoing area of research. Together, these mysteries highlight the intricate and dynamic nature of galaxies and underscore the need for sophisticated observations, simulations, and theoretical advancements to unravel the full story of galactic evolution. Star formation, the process by which dense regions of molecular clouds collapse to form stars, is rich with complexities and unanswered questions. One of the primary unknowns involves the initial conditions and specific triggers that set star formation in motion. While it's established that regions within molecular clouds must reach high densities and low temperatures to begin collapsing under their own gravity, the precise mechanisms that drive these conditions, whether it be turbulence, magnetic fields, or external pressures such as shock waves from supernova, are still a topic of active debate. Understanding these initial triggers is essential for piecing together the life cycle of stars and the evolution of galaxies. Another intriguing mystery focuses on the formation of massive stars. These stars, with masses more than 8 times that of our Sun, pose a particular challenge because their intense radiation and powerful stellar winds should, in theory, inhibit further material from accreting onto the nascent star. However, massive stars do form, implying that there are processes at play that allow for the accumulation of such large amounts of mass. Theories suggest that mechanisms like disk accretion, where material spirals into the star along a rotating disk, and competitive accretion within dense stellar clusters might be involved. Yet observational evidence to fully support or refine these models is still required. The initial mass function, IMF, which describes the distribution of masses for a population of newly formed stars, is another area shrouded in uncertainty. The IMF appears to follow a specific pattern universally, with many more low-mass stars forming compared to high-mass stars. However, the reasons behind this distribution and whether the IMF varies significantly under different environmental conditions remain topics of intense study. Insights into the IMF could provide critical information on the formation and evolution of stellar populations and their impact on galactic dynamics and chemical evolution. Magnetic fields and their role in star formation add another layer of complexity. While it is known that magnetic fields exist within molecular clouds, their influence on the fragmentation of clouds and the subsequent stages of star formation is not well understood. Magnetic fields might support clouds against gravitational collapse or guide the flow of material, but capturing the exact nature and strength of these fields involves challenging observations and simulations. Feedback processes from young stars, such as stellar winds, radiation pressure, and supernova explosions, also significantly impact star formation. These feedback mechanisms can either trigger subsequent star formation by compressing nearby gas or hinder it by dispersing surrounding material. Balancing these opposing effects and understanding how they regulate star formation rates across different environments remains an ongoing challenge. Furthermore, the process of forming planetary systems alongside stars introduces additional intricacies. How protoplanetary disks evolve and give rise to planets in tandem with the host star's development involves complex interactions of gas, dust, and gravitational dynamics, many aspects of which are not yet fully understood. The suite of unknowns in star formation, from the initial triggering mechanisms and the complexities of massive star formation to the role of magnetic fields, feedback processes, and the IMF, underscores the rich and intricate nature of this fundamental cosmic process. Continuous advancements in observational technology, theoretical modeling, and computational simulations are essential for unraveling these mysteries and achieving a comprehensive understanding of how stars and their accompanying planetary systems come to be. When observing the night sky, different types of stars, each of varying mass, temperature, and luminosity, pose their own fascinating mysteries. Take, for instance, neutron stars, the incredibly dense remnants of supernova. These stars, packing a sun's worth of mass into a city-sized sphere just about 12 miles across, wield magnetic fields trillions of times stronger than Earth's. They often emit pulsating beams of radiation as pulsars, and the enigmatic behavior of these pulses challenges astronomers to unravel the nature of matter under such extreme conditions. Neutron stars also occasionally merge, resulting in collisions that send ripples across space-time, gravitational waves detected here on Earth. The precise mechanisms driving the formation of these colossal waves remain an area of intense research. Then there are the much more massive black holes, stellar corpses so dense that not even light can escape their gravitational pull. These enigmatic entities can be elusive, revealed primarily through their interaction with surrounding matter or through gravitational lensing, a bending of light caused by their intense gravitational field. Black holes of varying sizes, from stellar mass to supermassive ones residing at the center of galaxies, challenge our understanding of gravity and quantum mechanics. They spark questions. How do they form exactly? What happens at the event horizon, the boundary beyond which no information can escape? Moreover, supermassive black holes influence the evolution of galaxies, yet the interplay between these cosmic giants and their host galaxies is still poorly understood. Such questions drive astronomers and physicists to continually push the boundaries of observational technology and theoretical physics. Supernovae, the spectacular and cataclysmic deaths of stars, are like cosmic fireworks that illuminate both the splendor and the mysteries of the universe. These colossal explosions scatter elements forged in the heart of stars, such as carbon, oxygen, and iron across the cosmos, seeding future generations of stars and planets. One of the most intriguing aspects of supernovae is the precise mechanism driving these detonations. For core collapse supernovae, which occur when massive stars exhaust their nuclear fuel and their cores implode, there's an interplay of extreme temperatures, pressures, and nuclear reactions that is not yet fully understood. Despite detailed computer simulations and theoretical models, we don't completely grasp how the shockwave that results leads to the supernova explosion visible from light years away. These stellar explosions also give rise to compact objects, either neutron stars or black holes, depending on the mass of the original star. The transition from the collapse of a star's core to the formation of such dense objects is shrouded in mystery. There's also the curious case of type Ia supernovae, which result from the thermonuclear explosion of a white dwarf in a binary system. These standard candles, crucial for measuring cosmic distances, still puzzle astronomers regarding their exact triggering conditions and variations. Understanding supernovae more deeply could unlock secrets about the rate of expansion of the universe, the distribution of elements, and even the behavior of matter under the most extreme conditions imaginable. Each supernova represents a fleeting opportunity for profound discovery, a bright blaze of light from which countless cosmic insights can be gleaned. Neutron stars, fascinating remnants of supernova explosions, present several unexplained and riveting properties that continue to baffle scientists. One of the most striking mysteries is their incredible density. Imagine cramming the mass of our Sun into a sphere only about 12 miles in diameter. The result is a state of matter so dense that a sugar cube-sized amount would weigh as much as a mountain. This density leads to extreme pressures and temperatures, creating conditions that are impossible to replicate on Earth. The composition of neutron stars, often described as a soup of neutrons possibly mixed with exotic particles like quark-gluon plasma, challenges our understanding of nuclear physics. How matter behaves under such immense pressure, and whether there are even more exotic forms of matter within the core, remains a topic of intense speculation and study. Another perplexing property is the intense magnetic field of some neutron stars known as magnetars. These fields can be trillions of times stronger than Earth's and can cause starquakes, sudden crustal movements that release vast amounts of energy and radiation. The exact mechanism behind these magnetic fields and their incredible strength is still not well comprehended. Additionally, neutron stars can spin at astonishing rates, with some rotating several hundred times per second. These pulsars emit beams of electromagnetic radiation from their magnetic poles that sweep across the sky like lighthouse beams, creating a rhythmic pulsation observable from Earth. The relationship between their rotation period, magnetic field, and emission of radiation offers another rich area of inquiry, aiming to clarify processes that govern the dynamics and life cycle of these enigmatic stellar remnants. Pulsars, the highly magnetized rotating neutron stars that emit beams of electromagnetic radiation, are known for their extraordinarily precise timing. This precision can be likened to a cosmic lighthouse, with beams sweeping across the universe in a rhythmic and predictable fashion. The key to this timing lies in the extraordinary stability of the neutron star's rotation. Despite their extreme environments, which include immense gravitational forces and magnetic fields, neutron stars maintain a remarkably consistent spin. This is in part due to their immense mass and compact size, which render them resilient to external disturbances that would otherwise alter their rotation. Moreover, the precise timing is also a result of the emission mechanisms. As the neutron star spins, its magnetic poles, where the beams of radiation are emitted, are fixed in location relative to the rotation axis. This means that the pulsation pattern we observe from Earth remains regular as long as the rotational period stays constant. Additionally, the conservation of angular momentum in these dense objects ensures that any changes in rotation are minimal over short timescales. Over longer periods, gradual energy losses due to electromagnetic radiation and particle wind cause the pulsars to spin down or slow their rotation. But even this deceleration is predictable and can be exquisitely measured. This timing precision makes pulsars invaluable cosmic clocks, with practical applications ranging from testing the theory of general relativity to searching for gravitational waves. Any irregularities in the pulsation timing can signal external influences such as orbiting planets or the gravitational wave passage, thus offering insights into phenomena otherwise difficult to detect. The study of pulsars, therefore, not only deepens our understanding of neutron stars, but also opens new windows into the broader workings of the cosmos. Black holes, the enigmatic endpoints for many massive stars, are steeped in mysteries that have captivated scientists and the public alike. When a star with sufficient mass exhausts its nuclear fuel, it can no longer sustain the outward pressure needed to counteract gravitational collapse. The result is a black hole. an object with a gravitational pull so strong that not even light can escape its grasp. One of the most profound mysteries surrounding stellar black holes is what happens at the event horizon, the boundary beyond which all information is lost to the outside universe. The event horizon poses a unique challenge to our understanding of physics, blending the principles of general relativity and quantum mechanics in ways that remain paradoxical and unresolved. How these two foundational theories coexist, or fail to do so, within the extreme environments of black holes is an open question that drives much of theoretical physics. Another captivating enigma is the formation process itself. How exactly do black holes emerge from supernovae, and what role do these events play in the evolution of galaxies? Observational data suggest that black holes can be found at the centers of most, if not all, galaxies, often as supermassive black holes millions or even billions of times the mass of our Sun. Yet, there is much left to understand about the growth mechanisms of these cosmic giants. Do small black holes merge over time to form supermassive ones? Or do massive stars in dense stellar environments collapse directly into these behemoths without a supernova explosion? Adding to this, the detection of gravitational waves from black hole mergers opens a new observational window, yet it also raises questions about how such binaries form and evolve. Moreover, the information paradox, famously posited by Stephen Hawking, questions what happens to the information contained in matter and energy that crosses the event horizon. According to quantum mechanics, information should never be lost, yet black holes seemingly erase it, challenging our fundamental understanding of physics. These enigmas make black holes not just astronomical oddities, but central to some of the greatest unresolved questions in modern science. Black holes, the quintessential cosmic enigmas, hold within them some of the universe's greatest mysteries, defying our current understanding of physics and cosmology. One of the most perplexing is the nature of the singularity that lies at the heart of a black hole. According to general relativity, a singularity is a point where gravitational forces compress matter to infinite density and zero volume. This concept challenges the fundamental principles as we know them, suggesting a breakdown of the laws of physics. The union of general relativity and quantum mechanics is expected to provide a more comprehensive theory of quantum gravity that could explain these singularities, but such a theory remains elusive. Another profound mystery is the black hole information paradox, which was famously highlighted by Stephen Hawking. This paradox arises from the apparent conflict between general relativity and quantum mechanics concerning the fate of information that falls into a black hole. According to general relativity, anything crossing the event horizon is permanently lost to the outside universe. However, quantum mechanics dictates that information cannot be destroyed. Hawking radiation, a theoretical prediction that black holes emit radiation and thus can eventually evaporate, compounds this paradox by suggesting that the information swallowed by a black hole could be lost forever as the black hole disappears, challenging the very principles of quantum theory. Additionally, the formation and growth of supermassive black holes, some of which possess masses billions of times that of our Sun, remain an area shrouded in mystery. How did these giants form so early in the universe's history, and what processes govern their rapid growth? Current models struggle to account for the existence of such massive entities in young galaxies. The merging of smaller black holes or direct collapse models are proposed explanations, but observational evidence and theoretical clarity are still lacking. Moreover, the edges of black holes, known as event horizons, pose another puzzle. What happens to particles and information at this boundary? Do they enter a state that we can never observe, becoming part of an information cloud paradoxically lost but not destroyed? These questions are at the frontier of modern physics, compelling researchers to devise new approaches and technologies to probe these cosmic mysteries. Black holes, thus, are not merely astronomical objects, but windows into the most profound questions about the universe's nature and the laws governing it. Black holes form and evolve through processes that are both awe-inspiring and complex, often rooted in the life cycles of massive stars. Stellar mass black holes, those with a mass ranging from a few to tens of times that of our Sun, typically originate from the violent deaths of massive stars in supernova explosions. When a star with a mass more than approximately 20 times that of the Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core collapses under its own gravity, and if the remaining mass is sufficient, it compresses into a singularity encased within an event horizon, the defining boundary of a black hole. The mechanisms driving the core collapse, from neutron degeneracy pressure to the role of neutrinos, are areas of active research, striving to detail how exactly this process catalyzes the formation of a black hole. Beyond stellar mass black holes, there exist supermassive black holes which inhabit the centers of most galaxies, including our own Milky Way. These giants, with masses ranging from millions to billions of solar masses, raise fascinating questions about their formation and growth. Unlike their smaller counterparts, supermassive black holes likely formed not from single stellar events, but through a combination of processes in the early universe. One hypothesis suggests that they grew from the mergers of smaller black holes and the accretion of vast amounts of gas and dust over time. Another theory posits that they might have formed from the direct collapse of massive primordial gas clouds without ever passing through a stellar phase. Observations of quasars, extremely luminous active galactic nuclei powered by supermassive black holes, indicate that some of these behemoths were already in place less than 1 billion years after the Big Bang, suggesting rapid growth mechanisms are at play. The evolution of black holes continues as they interact with their environment, accreting surrounding matter, merging with other black holes, or even being perturbed by tidal forces and interactions with stars and gas clouds. This accretion process is often spectacular, forming an accretion disk of infalling material that heats up and emits powerful radiation, sometimes producing relativistic jets of particles that can extend thousands of light years. Additionally, the detection of gravitational waves from black hole mergers has opened a new window into studying these enigmatic objects, allowing scientists to observe the final moments of such cataclysmic events and further understand the dynamics governing their evolution. As our observational tools and theoretical models advance, the intricate life cycles of black holes reveal ever more about the cosmos's hidden depths and the fundamental forces shaping it. The universe is home to various types of black holes, each with distinct and yet to be fully understood characteristics that present a treasure trove of cosmic mysteries. Stellar mass black holes, typically formed from the collapse of massive stars, are the most well-known but still enigmatic. One major unknown is the exact nature of the material inside the event horizon. While general relativity predicts a singularity, a point where density becomes infinite, quantum mechanics suggests there may be exotic states of matter at play, potentially revealing new physics beyond our current theories. Furthermore, the dynamics of black hole mergers, now observable through gravitational wave signals, raise questions about the properties of the resultant black hole, such as its spin and how the energy from the merger is distributed. Intermediate mass black holes, theorized to be thousands to hundreds of thousands of solar masses, are even more mysterious due to their elusive nature. These black holes could serve as the missing link in our understanding of black hole formation, bridging the gap between stellar mass and supermassive black holes. However, their scarcity and the difficulty in detecting them leave open questions about their origin. Are they the product of successive mergers of stellar mass black holes, or do they form in dense star clusters through other yet unknown processes? Supermassive black holes, residing at the centers of most galaxies, present some of the most profound mysteries in modern astrophysics. One major enigma is how they grow so rapidly in the early universe. Observations of quasars, extremely luminous objects powered by accretion onto supermassive black holes, suggest that some of these giants reached billions of solar masses within a few 100 million years after the Big Bang. This rapid growth exceeds what many current models can easily explain, pointing to potentially unknown mechanisms of mass acquisition or the presence of much larger seed black holes than previously thought. Additionally, the environments around supermassive black holes, often marked by accretion disks and relativistic jets, are intricate and poorly understood. These regions are incredibly energetic and dynamic, yet the physics governing the interaction between the black hole, its accretion disk, and surrounding magnetic fields remains an active area of research. Each type of black hole represents a different facet of the cosmos's dark heart, holding clues to fundamental forces and processes that sculpt the universe, manifesting some of the most compelling puzzles in all of science. Beyond the event horizon of a black hole lies a realm filled with some of the most tantalizing and perplexing mysteries in modern astrophysics and theoretical physics. The event horizon itself is a boundary beyond which nothing, not even light, can escape the gravitational grip of the black hole. Once this threshold is crossed, conventional understanding of space and time breaks down. One of the greatest puzzles is the nature of the singularity at the black hole's core where, according to general relativity, matter is crushed to infinite density and the curvature of space-time becomes infinitely large. This singularity represents a point where our physical laws cease to function, pushing the limits of general relativity and demanding a new theory that can coherently integrate gravity with quantum mechanics. The fate of information that falls into a black hole is another profound enigma. Known as the information paradox, this conundrum arises from the conflict between general relativity and quantum mechanics. In quantum mechanics, information about physical states is supposed never to be lost. However, if objects crossing the event horizon are forever trapped, it seems that their information is lost to the universe. Stephen Hawking's proposition that black holes can emit radiation and eventually evaporate, known as Hawking radiation, further complicates this puzzle. If a black hole evaporates entirely, what happens to the information it has consumed? This question remains one of the most critical, unsolved issues in theoretical physics, spurring ideas ranging from holographic principles to the existence of firewalls, hypothetical phenomena where infalling information is incinerated at the event horizon. The internal structure of a black hole is also shrouded in mystery. While it's common to imagine black holes as having a simple, spherical geometry, solutions to Einstein's equations suggest that rotating black holes, or Kerr black holes, should have more complex interiors. These might include structures like inner and outer event horizons and regions of frame dragging, where space itself is twisted by the black hole's rotation. Theoretical models and simulations suggest that at extreme levels of rotation and mass, the interior of black holes could reveal even stranger states of space-time, possibly harboring wormholes or even gateways to other regions of the universe. Lastly, the concept of entropy and thermodynamics within black holes adds another layer of mystery. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not their volume, suggesting profound insights about the fabric of space-time itself. If black holes can be described thermodynamically, what does that imply about the nature of space-time and gravity? Unraveling these mysteries could lead to groundbreaking discoveries, offering a deeper understanding of the universe and the fundamental laws that govern it. The true nature of a black hole's singularity is one of the most profound and elusive mysteries in astrophysics. A singularity, as predicted by general relativity, is a point where gravitational forces become infinitely strong, causing space and time to curve infinitely. In this scenario, the density of matter and the gravitational pull become so intense that our current understanding of physics breaks down. This infinite curvature of space-time suggests a place where the known laws of general relativity and quantum mechanics no longer apply, demanding a unified theory of quantum gravity to provide a clear picture. One of the central challenges in understanding the singularity is reconciling general relativity with quantum mechanics. General relativity governs the macroscopic world of stars, galaxies, and black holes, while quantum mechanics describes the microscopic world of particles and forces. At a singularity, where densities become extreme, these two realms collide. Several theories attempt to bridge this gap, with string theory and loop quantum gravity being among the leading candidates. String theory, for instance, posits that particles are one-dimensional strings rather than point particles, which could potentially smooth out the infinite densities of a singularity. Loop quantum gravity, on the other hand, suggests that spacetime itself has a discrete structure at the smallest scales, again potentially avoiding the infinities predicted by general relativity. Beyond theoretical frameworks, the singularity's nature raises fundamental questions about the fate of information and the ultimate structure of spacetime. The information paradox, brought to the forefront by Stephen Hawking, contends with what happens to the information about the physical state of objects that fall into the black hole. If these objects are compressed into a singularity, is the information about them lost forever? This paradox contradicts quantum mechanics, which asserts that information must be conserved. Resolving this paradox could revolutionize our understanding of both quantum theory and gravitational theory. Additionally, some leading-edge ideas such as the holographic principle imply that all the information contained within a volume of space can be described by information on the boundary of that space. In the context of black holes, this means the information swallowed by a black hole might be encoded on its event horizon, leading to potential insights about the nature of black holes and singularities. The true essence of a black hole's singularity remains a frontier in modern science, symbolizing the limits of our knowledge and the potential for groundbreaking discoveries. Unraveling this mystery not only promises to illuminate the internal structure of black holes, but also to reshape our understanding of the universe's most fundamental laws. Black holes exert influence over their surroundings in profoundly complex ways that are still not fully understood, thus presenting a fertile ground for scientific exploration. One of the key aspects of this influence is the interaction between black holes and their surrounding matter, especially through the accretion process. As matter forms an accretion disk around a black hole, it spirals inward, heating up to extreme temperatures and radiating copious amounts of energy, often outshining entire galaxies. The mechanisms that drive this accretion and the resultant outflow of energy are not completely understood, particularly the role of magnetic fields in channeling material and launching relativistic jets. These jets, which can extend thousands of light years, influence star formation and the interstellar medium in their host galaxies, but the exact physics governing their formation and evolution remain a topic of intense investigation. Another intriguing mystery is the dynamic relationship between supermassive black holes at galactic centers and their host galaxies. Observations suggest a correlation between the mass of these central black holes and certain properties of the galaxies, such as the velocity dispersion of stars in their bulges, a relationship known as the M-sigma relation. How supermassive black holes grow and regulate their environments to establish this correlation is not entirely clear. Some theories propose feedback mechanisms where energy and momentum from the accretion process and emitted jets regulate the growth of both the black hole and the galaxy by heating and expelling gas that would otherwise form new stars. However, the details of these feedback processes and their efficiency across different evolutionary stages of galaxies are still poorly understood. Gravitational waves, ripples in space-time caused by cosmic cataclysms like black hole mergers, are another emergent area unveiling the far-reaching influence of black holes. The detection of these waves has opened a new observational window, allowing us to study events and environments that are otherwise inaccessible. Yet, the full implications of these gravitational waves remain largely unknown. For instance, how frequent are these mergers, and what do they tell us about the populations and evolution of black holes across the universe? There's also the question of how these waves might impact the surrounding space-time, potentially carrying information about the regions they traverse. In addition, there are peculiar phenomena such as black hole spin and the effect of frame dragging, where the rotation of a black hole can twist the fabric of space-time around it. This intricate interaction affects the orbits of nearby objects and the behavior of the accretion disk. Understanding the precise effects of these dynamics is crucial for interpreting high-energy astrological phenomena. Collectively, these unexplored influences signify that black holes are not merely endpoints of stellar evolution, but active participants in the cosmic dance, shaping and reshaping their environments in ways that continue to both intrigue and confound scientists. Further advancements in observational technology and theoretical frameworks promise to shed light on these enigmatic interactions, broadening our comprehension of the universe. Yes, we can observe black hole mergers, and these observations are unlocking a plethora of mysteries that challenge our understanding of the cosmos. One of the primary ways we detect black hole mergers is through gravitational waves, ripples in spacetime predicted by Einstein's general theory of relativity and first directly observed by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. These waves are generated by some of the most violent events in the universe, such as the collision and subsequent merging of black holes. The signals picked up by LIGO and its European counterpart Virgo have already provided insights into the mass and spin of black holes and hinted at the formation channels of binary black hole systems. Despite these groundbreaking discoveries, many mysteries surround black hole mergers. One key question is how these black hole binaries form in the first place. Are they born together as a binary system of massive stars that eventually collapse into black holes? Or are they formed through dynamic interactions in dense stellar environments like globular clusters? Each formation pathway has different implications for the properties and frequencies of the black hole mergers we observe. The spin alignments of the merging black holes, for instance, can indicate whether they originated from binary star systems, or if they were captured later through gravitational interactions in dense star clusters. Moreover, the final merger product, typically a more massive black hole, also poses intriguing questions. When the black holes merge, they emit gravitational waves that carry away energy and angular momentum, causing the new black hole to ring down to a stable state. This post-merger phase can potentially reveal details about the newly formed black hole's structure and properties. However, the exact profile of this ringdown and the information it carries are subjects of active research. Understanding these ringdown signatures could help test general relativity in the strong field regime, offering insights into quantum gravitational effects. Another captivating mystery is whether these black hole mergers can produce identifiable electromagnetic counterparts, such as gamma-ray bursts. While black holes themselves do not emit light, the scenarios right before or after a merger could involve interactions with surrounding matter, potentially producing observable electromagnetic signals. Confirming such emissions could open a multi-messenger astronomy era, where gravitational waves and electromagnetic signals together provide a fuller picture of cosmic events. OAT. Finally, there is the larger question of dark matter and its potential relationship to black hole mergers. Some theories suggest that a fraction of black hole mergers could involve primordial black holes, which formed in the early universe and could account for some or all of dark matter. Observing more black hole mergers and understanding their mass distribution could shed light on this possibility, fundamentally altering our understanding of the universe's composition. These mysteries make black hole mergers not just an observational breakthrough, but a cosmic puzzle piece, offering clues that may lead to some of the most profound discoveries in modern astrophysics and cosmology. As we refine our detection capabilities and theoretical models, the secrets held by these colossal collisions continue to inspire and challenge us. Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in 1974, fundamentally challenges our understanding of black holes and the laws of physics governing them. According to classical general relativity, nothing can escape a black hole's gravitational pull once it crosses the event horizon. However, Hawking proposed that black holes can emit radiation due to quantum mechanical effects near the event horizon, suggesting that black holes are not completely black, but can slowly lose mass and energy over time. Hawking radiation arises from the peculiar behavior of quantum fields in curved spacetime. In the vacuum near the event horizon, particle-antiparticle pairs spontaneously appear and typically annihilate each other almost immediately. However, if this process occurs near the event horizon, one particle could fall into the black hole while the other escapes into space. To an outside observer, it appears as if the black hole is emitting radiation. This escaping particle effectively reduces the mass and energy of the black hole, leading to a slow process known as black hole evaporation. One of the most profound challenges posed by Hawking radiation is the so-called information paradox. In quantum mechanics, information about a physical system's state is preserved over time, a principle known as unitarity. However, if a black hole can completely evaporate via Hawking radiation, all information about the matter that fell into it seemingly disappears, violating the unitarity principle. This paradox suggests a fundamental conflict between general relativity and quantum mechanics, indicating that our current theories might be incomplete or require significant revision to be reconciled. The concept of Hawking radiation also introduces thermodynamic properties to black holes. implying that they possess entropy and temperature encapsulated by the laws of black hole thermodynamics. The entropy of a black hole is proportional to the area of its event horizon, rather than its volume, which is a startling revelation that hints at a deeper connection between gravity, thermodynamics, and quantum theory. This relationship raises questions about the microscopic states that account for the black hole's entropy, and whether a quantum theory of gravity can naturally incorporate these aspects. Additionally, Hawking radiation has profound implications for the ultimate fate of black holes, particularly small black holes which can evaporate completely in a relatively short cosmological timescale. Theoretical models often extrapolate these concepts to primordial black holes formed in the early universe, which could evaporate today, potentially explaining various astrophysical phenomena or even contributing to our understanding of dark matter. While direct observational evidence for Hawking radiation remains elusive, upcoming advancements in observational techniques and space-time detectors might provide indirect clues, thereby testing Hawking's groundbreaking prediction. This radiation remains a cornerstone for theorists aiming to bridge the divide between quantum mechanics and general relativity, propelling us toward a more unified understanding of the universe. Dark matter is one of the most enigmatic components of the universe, constituting approximately 27% of its total mass and energy content, yet remaining undetectable by conventional astronomical observations. Unlike ordinary matter, which interacts with electromagnetic forces and is therefore visible through telescopes in the form of stars, gas, and dust, dark matter does not emit, absorb, or reflect light. This invisibility makes dark matter detectable only through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The concept of dark matter emerged from numerous observational discrepancies. One of the earliest pieces of evidence came from studies of galaxy rotation curves. In the 1970s, astronomer Vera Rubin discovered that the outer regions of galaxies rotate at much higher velocities than could be accounted for by the visible mass alone. According to Newtonian dynamics, galaxies should fly apart unless there is additional unseen mass providing the necessary gravitational pull to hold them together. This unseen mass was theorized to be dark matter. Further evidence came from gravitational lensing, where light from distant objects is bent around massive objects. The amount of lensing observed often exceeds what would be expected based on visible mass, implying the presence of additional mass in the form of dark matter. Why then is dark matter so elusive? One reason lies in its weak interactions with ordinary matter. Dark matter is thought to interact primarily through gravity and possibly via weak nuclear forces, but not through electromagnetic or strong nuclear forces. This lack of interaction with light and other forms of electromagnetic radiation means that dark matter cannot be seen using traditional telescopes, nor can it be detected directly by the electromagnetic detectors on Earth. Various experiments are underway to detect dark matter particles indirectly or through their interactions with standard particles, but conclusive results have yet to be achieved. Another reason for its elusiveness is that we do not yet understand its precise nature. Several theories propose what dark matter could be, including weakly interacting massive particles, WIMPs, axions, or sterile neutrinos. Each of these candidates requires specific interactions and properties, guiding the design of experiments attempting to detect them. For instance, WIMPs are hypothesized to have masses much heavier than protons and would interact via weak nuclear forces, making them detectable in highly sensitive underground detectors that minimize background noise from cosmic rays. In addition to particle candidates, there are theoretical frameworks suggesting dark matter could consist of primordial black holes or other non-particle forms. Each hypothesis involves significant gaps in our understanding and introduces new sets of challenges for detection and study. Furthermore, dark matter plays a crucial role in the formation and evolution of cosmic structures. Its gravitational influence is thought to act as a scaffold for the formation of galaxies and clusters of galaxies, affecting the distribution of visible matter in the universe. Understanding dark matter is not merely an academic exercise. It impacts our comprehension of fundamental cosmic processes and the overall dynamics of the universe. Dark matter remains a tantalizing mystery owing to its non-interaction with light, unknown fundamental properties, and the current limits of detection technology. Continued advancements in experimental physics, astronomy, and cosmology are essential to unlock the secrets of this elusive yet fundamental constituent of the cosmos. Detecting dark matter, one of the most elusive substances in the cosmos, involves a multifaceted approach combining astrophysical observations, experimental physics, and theoretical models. Despite its invisibility to light, dark matter can be inferred through its gravitational effects and potential weak interactions with normal matter. Here are some primary methods researchers use to detect dark matter. One key approach is indirect detection, searching for byproducts of dark matter interactions or decay. These methods look for anomalous signals in cosmic rays, gamma rays, or neutrinos that might indicate dark matter particles annihilating or decaying into standard particles. The Fermi Gamma Ray Space Telescope, for example, scans the sky for gamma-ray emissions that could originate from dark matter annihilations in regions with high dark matter density, such as the galactic center. Similarly, ground-based Cherenkov telescopes like the Very Energetic Radiation Imaging Telescope Array System, VERITAS, detect high-energy particles and gamma rays that might be linked to dark matter interactions. Another prominent strategy is direct detection, which aims to observe dark matter particles as they interact with ordinary matter. Detectors are usually placed deep underground to shield them from cosmic rays and other background radiation that could mimic dark matter signals. These experiments typically involve large tanks filled with heavy elements like xenon or argon. When a dark matter particle collides with the nucleus of an atom in the detector, it causes the nucleus to recoil, producing a small detectable amount of light or ionization. Experiments such as the Large Underground Xenon, LUX experiment, its successor LUX-Zeppelin, LZ, and the Xenon 1T experiment represent frontline efforts in this area. There are also collider-based searches for dark matter, specifically using particle accelerators like the Large Hadron Collider, LHC, at CERN. In these experiments, physicists collide protons at high energies, hoping to create dark matter particles directly. Because dark matter particles would not interact electromagnetically, they would escape the detector unnoticed. But their presence can be inferred from an apparent imbalance in momentum and energy in the collision products, often referred to as missing energy signatures. Astrophysical and cosmological observations also provide essential clues. The study of the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, offers insights into the early universe's composition. Observations from the Planck satellite have provided precise measurements of the CMB, helping to constrain the amount and distribution of dark matter. Additionally, gravitational lensing, where light from distant objects is bent by the gravitational field of massive foreground objects, reveals the distribution of dark matter in galaxies and clusters. Surveys like the Dark Energy Survey, DES, map out these lensing effects to infer the underlying dark matter structure. Each of these methods has its unique challenges and limitations, but together they offer a multi-pronged approach to unravel the mysteries of dark matter. As technology advances and new observational data accumulate, these complementary strategies bring us ever closer to understanding the nature of this mysterious component of the universe. The ongoing pursuit of dark matter detection not only aims to identify a specific particle or interaction, but also strives to integrate this knowledge into a comprehensive framework for the fundamental workings of the cosmos. Dark energy is one of the most profound enigmas in cosmology today. Despite being thought to make up about 70% of the total energy content of the universe, its true nature remains elusive and mysterious. Dark energy is theorized to be responsible for the accelerated expansion of the universe, a phenomenon first observed in the late 1990s through Type Ia supernovae studies. This discovery was nothing short of groundbreaking, overturning the previously held belief that the expansion of the universe should be slowing down due to the gravitational pull of its own matter. Scientists describe dark energy as a sort of anti-gravity, a repulsive force that pushes galaxies apart and stretches the fabric of space-time. One of the biggest questions scientists grapple with is whether dark energy is a property of space itself or if it represents a new, unknown form of dynamic energy fluid. The cosmological constant, introduced by Einstein in his equations of general relativity, initially as a mistake, is one candidate. It's a constant energy density filling space homogeneously. However, another intriguing possibility is that dark energy could be a new dynamical field that changes over time and space, known as quintessence. Despite extensive observational efforts using space telescopes, ground-based observatories, and the cosmic microwave background radiation data, the exact nature of dark energy continues to escape our full understanding. The quest to unlock its secrets compels us to push the boundaries of our knowledge, leading to new technological advancements and potentially revolutionary scientific theories. Dark energy exerts a remarkable influence on the expansion of the universe by acting as a repulsive force, counteracting the attractive pull of gravity. Discovered through observations of distant Type Ia supernovae in the late 1990s, this phenomenon showed that the universe's expansion is not just continuing, but accelerating. This acceleration means galaxies are moving away from each other at an ever-increasing pace, a revelation that has upended our understanding of the cosmos. Essentially, dark energy is thought to permeate all of space, working uniformly to push the universe apart. As a result, its influence becomes more dominant as the universe expands, meaning the repulsive force grows stronger relative to gravitational forces over cosmic time. One way to conceptualize this is to imagine space itself as an inflating balloon. In the early universe, the effects of dark energy were relatively negligible compared to the gravitational clumping of matter forming stars, galaxies, and larger structures. However, as the balloon expands, dark energy starts to dominate, stretching space at an increasing rate. This accelerated expansion has profound implications for the fate of the universe. If dark energy continues to drive expansion indefinitely, we could be headed towards a big freeze, where galaxies drift so far apart that stars eventually burn out, and the universe becomes cold and dark. Some theories even suggest a big rip, where dark energy becomes so powerful that it tears apart galaxies, stars, and eventually atomic matter itself. Understanding dark energy, therefore, is not just about comprehending our current universe. It is about predicting its ultimate destiny. Dark matter, another cornerstone of modern cosmology, remains one of the universe's most enigmatic components. Unlike dark energy, dark matter does not interact with electromagnetic forces, which means it doesn't emit, absorb, or reflect light, making it invisible directly to our telescopes. However, its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter is thought to comprise about 27% of the universe's total mass and energy content. One of the leading theories about its nature posits that it consists of weakly interacting massive particles, or WIMPs. These hypothetical particles are believed to interact only through the gravitational force and possibly the weak nuclear force, hence their elusive nature. Another compelling theory suggests the existence of axions, which are incredibly light particles that could also account for dark matter. Unlike WIMPs, axions are theorized to interact minimally even with the weak nuclear force, making their detection exceedingly challenging. Other candidates include sterile neutrinos and primordial black holes, each offering intriguing explanations but facing significant hurdles in observational verification. While particle accelerators like the Large Hadron Collider and various direct detection experiments buried deep underground have yet to provide definitive evidence, they continue to refine our understanding and narrow down the possibilities. The search for dark matter is a testament to human curiosity and ingenuity, driving the development of new technologies and inspiring theoretical breakthroughs. The quest to uncover the true nature of dark matter not only seeks to explain 27% of the universe, but also aims to resolve fundamental questions about the formation and evolution of cosmic structures, from galaxies to galaxy clusters. Dark energy, the mysterious force driving the accelerated expansion of the universe, raises several profound and perplexing questions. One of the most significant mysteries is its fundamental nature. Scientists debate whether dark energy is a constant property of space, known as the cosmological constant, or if it represents a dynamic force that evolves over time. The cosmological constant, first introduced by Einstein, suggests a uniform energy density that remains the same throughout the universe's expansion. In contrast, dynamic theories such as quintessence propose that dark energy might change in intensity and distribution across the cosmos, potentially altering the rate of expansion differently over time. Another critical question revolves around the origin and mechanism of dark energy. Why does dark energy exist, and how did it come to dominate the universe's expansion only relatively recently in cosmic history? This leads to inquiries about whether dark energy is linked to one of the known forces of nature, or if it represents a completely new fundamental force. Additionally, the ultimate fate of the universe under the influence of dark energy poses another monumental question. Will the accelerated expansion continue indefinitely, leading to a cold, desolate Big Freeze? Or could it escalate into a catastrophic Big Rip, where galaxies, stars, and even atomic particles are torn apart? Addressing these questions not only requires breaking ground in theoretical physics, but also demands innovative observational techniques to gather more precise data. The answers to these questions could fundamentally alter our understanding of the universe and the laws governing it, pushing the boundaries of cosmology into uncharted territory. Dark matter and dark energy collectively represent some of the most profound challenges to our understanding of physics. These mysterious components are thought to make up approximately 95% of the universe, yet they remain largely undetected and unexplained by our current theories. Their elusive nature casts doubt on the completeness of the standard model of particle physics, which does not account for these dark entities. Dark matter, for instance, appears to interact primarily through gravity, clumping together to form the scaffolding upon which galaxies and larger cosmic structures are built. However, it does not emit, absorb, or reflect light, making it invisible to traditional observational methods. This discrepancy suggests that there could be an unseen, dark sector of particles and forces that we have yet to discover, prompting physicists to consider extensions or modifications to existing theoretical frameworks. Dark energy, on the other hand, challenges our understanding of gravitation and the behavior of the universe on the largest scales. The concept of a repulsive force driving the accelerated expansion of the universe was a radical addition to Einstein's equations of general relativity, originally introduced as the cosmological constant. However, if dark energy is not constant but rather dynamic, it could imply the existence of new fields or forces that have so far eluded detection. This has led to speculation about the quintessence field or other exotic mechanisms that could drive cosmic acceleration. The discovery of dark energy has also raised questions about the ultimate fate of the universe, introducing scenarios like the Big Freeze or Big Rip, which challenge our preconceived notions of cosmic destiny. These challenges compel physicists to explore new models that might integrate these dark components into a more comprehensive theory of the universe, potentially leading to revolutionary advancements in our understanding of fundamental physics. The expanding universe presents a multitude of mysteries that captivate cosmologists and astrophysicists alike. One of the most fundamental questions is the nature and fate of the universe's expansion. Despite initially being predicted by the Big Bang theory, the discovery that this expansion is accelerating due to dark energy adds a layer of complexity. This unexpected acceleration suggests that our understanding of gravity, as described by general relativity, might be incomplete or require modification when applied on cosmic scales. Additionally, the ultimate fate of the universe, whether it will end in a Big Freeze, Big Crunch, or a Big Rip scenario, is still a matter of intense speculation and debate. Another intriguing mystery lies in the measurement of the Hubble constant, which quantifies the rate at which the universe is expanding. Different observational methods yield slightly varying results, a discrepancy known as the Hubble tension. For instance, measurements based on cosmic microwave background data and observations of distant supernova don't entirely align. Resolving this tension could either point to systematic errors in measurements or hint at new physics beyond our current models. Moreover, the initial conditions leading to the Big Bang and the very nature of time and space at that singularity are profound mysteries. What could have triggered the Big Bang? Was our universe born from an unstable quantum state, or could it be part of a multiverse, wherein multiple universes exist with varying laws of physics? These mysteries compel researchers to develop more sophisticated observational tools, like next-gen space telescopes and gravitational wave detectors, while also pushing theoretical physics into new, uncharted territories. Through these endeavors, we may not only answer some of these existing questions, but also uncover new phenomena that further expand our understanding of the cosmos. The concept of the expanding universe is supported by several key pieces of astrophysical evidence, each reinforcing the notion that the cosmos has been stretching and evolving ever since the Big Bang approximately 13.8 billion years ago. The first and most direct evidence comes from the redshift of light from distant galaxies, a phenomenon initially discovered by the American astronomer Edwin Hubble in the 1920s. Through meticulous observation, Hubble found that galaxies are receding from us at speeds proportional to their distance, a relationship now known as Hubble's law. This redshift occurs because as galaxies move away, the light waves they emit are stretched, shifting them towards the red end of the spectrum, much like the lowering of pitch as an ambulance siren moves away from you. Another compelling piece of evidence is the cosmic microwave background radiation, CMB, a faint glow permeating the universe that serves as the afterglow of the Big Bang. Discovered by Arno Penzias and Robert Wilson in 1965, the CMB provides a snapshot of the infant universe, showing us conditions from roughly 380,000 years after the Big Bang. The uniformity and slight anisotropies in this radiation support the notion that the universe has been expanding and cooling ever since its fiery inception. Additionally, detailed observations of large-scale structures in the universe, including the distribution of galaxies and galaxy clusters, match predictions made by the theory of an expanding universe. These structures form through hierarchical clustering, driven by gravity, in an ever-enlarging cosmic canvas. Further supporting this idea are supernova observations, particularly those involving Type Ia supernovae, which serve as standard candles due to their consistent luminosity. In the late 1990s, two independent research teams observed that these types of supernovae were dimmer than expected, implying that they were farther away than their redshift values alone would suggest. This groundbreaking discovery indicated not just expansion, but an accelerated expansion of the universe, thereby introducing the concept of dark energy. Each of these lines of evidence corroborates the view of a dynamic, ever-expanding universe, continually stretching the bounds of our understanding and curiosity about its origin, evolution, and ultimate fate. Redshift plays a crucial role in our understanding of the universe, acting as one of the key tools for astronomers and cosmologists to decipher the cosmos. Fundamentally, redshift refers to the phenomenon where light from objects in space, such as galaxies, is stretched to longer, redder wavelengths as the objects move away from us. This effect was first systematically catalogued by Edwin Hubble in the 1920s, leading to the formulation of Hubble's law. Hubble observed that the farther away a galaxy is, the faster it appears to be receding from us, providing the first direct evidence of the universe's expansion. This relationship between distance and velocity shifted the paradigm from a static universe to an expanding one, supporting the Big Bang theory, which posits that the universe began from a hot, dense state and has been expanding ever since. Beyond the broader understanding of cosmic expansion, redshift has practical applications that extend to measuring distances in the universe and understanding its structure and evolution. For instance, astronomers utilize redshift to determine the velocity at which galaxies and other celestial objects are receding from us. This measurement, when combined with distance data derived from other methods, allows scientists to map the large-scale structure of the universe and study the distribution of galaxies over cosmic time. Additionally, by analyzing the spectral lines of light from distant objects, astronomers can glean information about their composition, motion, and environment. More intriguingly, redshift aids in probing the very early universe. Observing the light from extremely distant galaxies, which has traveled for billions of years to reach us, essentially allows scientists to look back in time and study the conditions of the universe shortly after the Big Bang. This provides insights into galaxy formation and evolution, the behavior of dark matter, and the influence of dark energy on cosmic acceleration. Thus, redshift is not just a measure of distance or movement, it is a window into the past, a fundamental indicator of cosmological phenomena, and a pivotal element in our quest to comprehend the vast, expanding, and ever-mysterious universe. The expansion of the universe profoundly affects cosmic structures on both large and small scales, influencing everything from the distribution of galaxies and galaxy clusters to the behavior of cosmic voids and even the evolution of individual stars and galaxies. On the grandest scales, the universe's ongoing expansion causes the large-scale structure of the cosmos to evolve over time. In the early universe, matter was more uniformly distributed, but as the universe expanded, tiny quantum fluctuations in density grew under the influence of gravity. Over billions of years, these fluctuations coalesced into the vast cosmic web of galaxies and dark matter filaments we observe today. Within this expanding framework, galaxy clusters, which are the largest gravitationally bound structures in the universe, continue to grow by accumulating material from their surroundings. As the universe expands, galaxies within these clusters remain gravitationally bound to each other, but the space between clusters stretches, making the clusters appear to move away from each other. This expansion creates cosmic voids, vast regions with very few galaxies or matter, between clusters and superclusters. One significant effect of this expansion is the redshift of light from distant objects, which not only provides insights into the rate of expansion, but also affects observations of cosmic phenomena by shifting spectral lines and altering our interpretation of astrophysical data. On a smaller scale, the expansion of the universe impacts the formation and evolution of galaxies and stars. In a constantly expanding universe, the raw material for star formation, primarily hydrogen and helium gas, becomes more dispersed over time. This dilution influences the rate at which new stars can form in galaxies, affecting their growth and evolution. Additionally, as the universe expands, the residual heat from the Big Bang, observed as the cosmic microwave background radiation, continues to cool. This decrease in temperature affects the thermal history of the universe, which in turn influences the physical processes governing galaxy formation and the behavior of interstellar and intergalactic gases. Overall, the universe's expansion shapes the cosmic landscape in complex and interconnected ways. It drives the large-scale structure's growth, governs the dynamics within and between galaxy clusters, and influences the formation and evolution of galaxies and stars. Understanding this intricate dance requires detailed observations and sophisticated simulations, pushing the boundaries of astronomy, cosmology, and theoretical physics as we seek to unravel the mysteries of our ever-expanding universe. The ultimate fate of the universe is one of the most intriguing and speculative areas of cosmology, with several leading theories proposing different end scenarios based on our understanding of dark energy, dark matter, and the fundamental forces of nature. One of the primary theories is the Big Freeze or heat death, which posits that the universe will continue to expand indefinitely. In this scenario, the accelerated expansion driven by dark energy will cause galaxies to move farther apart, making star formation increasingly rare as the available interstellar gas becomes too diffuse. Over vast timescales, existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Eventually, even these remnants will decay, resulting in a cold, dark, and lifeless universe where temperatures approach absolute zero. Another potential outcome is the Big Crunch, a scenario where the expansion of the universe eventually halts and reverses. If dark energy is not constant but diminishes over time, or if it changes in such a way that gravity dominates again, the universe could reach a tipping point. The gravitational attraction of all the mass in the universe would cause it to contract, leading galaxies, stars, and eventually all matter to collapse back into an extremely hot and dense state, possibly akin to the conditions of the Big Bang. This cyclic model suggests that the universe could potentially go through endless cycles of expansion and contraction, although this idea faces significant challenges given current observations supporting the dominance of dark energy. A more extreme possibility is the Big Rip, which theorizes that dark energy's repulsive force might increase over time. If dark energy's influence grows stronger, it could reach a point where it overcomes all other forces, including gravity and the electromagnetic force that holds atoms together. The Big Rip would begin by tearing apart galaxy clusters, followed by individual galaxies, stars, planets, and eventually ripping apart atoms themselves into subatomic particles, effectively disintegrating the universe in a violent end. Lastly, some theories propose alternate fates involving quantum mechanics and concepts like the multiverse. For instance, quantum fluctuation models suggest that the universe might undergo phase transitions or tunneling events, leading to the formation of new, separate baby universes. These scenarios often rely on highly speculative and complex quantum theories that challenge our conventional understanding of space and time. Understanding which of these scenarios might play out depends on accurately determining the properties of dark energy, the overall curvature of the universe, and the interactions between its fundamental components. Future observations and theoretical advancements will be crucial in refining these theories and bringing us closer to understanding the ultimate fate of the cosmos. Exoplanets are planets that orbit stars beyond our Sun. These distant worlds come in a remarkable variety, some akin to our Earth, while others are vastly different, featuring exotic atmospheres and bizarre weather conditions. The discovery of exoplanets has dramatically expanded our understanding of the universe, offering new insights into planet formation and the potential for life beyond our solar system. The first confirmed exoplanet was discovered in 1992, orbiting a pulsar, a type of neutron star, in the constellation Virgo. Since then, advancements in technology have led to the identification of over 4,000 exoplanets, each contributing a piece to the cosmic puzzle. Astronomers employ several methods to detect these elusive celestial bodies, with two being particularly effective. The transit method relies on observing the slight dimming of a star's light when an exoplanet passes or transits in front of it. This technique can even reveal details about the planet's atmosphere and size. Another powerful method is the radial velocity, or Doppler method, which detects the wobbling motion of a star caused by the gravitational pull of an orbiting planet. These wobbles induce shifts in the star's spectral lines due to the Doppler effect, indicating the presence and mass of the unseen companion. Together, these methods have transformed our perception of the universe, bringing into focus the intricate ballet of star systems beyond our own. The study of exoplanets has unveiled numerous enigmatic phenomena that continue to baffle scientists. For instance, some exoplanets exhibit highly unusual orbits, defying conventional understanding of planetary dynamics. These exoplanets orbit their stars at extreme inclinations or in eccentric elliptical paths, rather than the near circular orbits typical in our solar system. Such irregularities suggest the presence of unseen forces or interactions, possibly involving additional planets or even a close encounter with a passing star that disrupted the system's stability. Moreover, some of these worlds are so close to their stars that they complete an orbit in mere days, leading to tidal forces that can significantly alter their structures and atmospheres in ways that we are only beginning to comprehend. Another perplexing phenomenon involves the atmospheres of certain exoplanets. There are cases where exoplanetary atmospheres exhibit strange chemical compositions that challenge our understanding of planetary science. For example, scientists have detected the presence of titanium oxide and vanadium oxide in the atmospheres of some hot Jupiter's gas giants that orbit very close to their stars. These molecules can create strong temperature inversions, dramatically affecting atmospheric dynamics and weather patterns. Additionally, some exoplanets show unexpected cloud formations composed of materials like silicates or even sand-like particles, resulting in exotic weather systems far removed from terrestrial experience. These peculiarities hint at complex processes that are not yet fully understood, spurring astronomers to delve deeper to unlock the secrets of these distant worlds. Exoplanets come in a fascinating array of types, each presenting its own set of scientific puzzles. Take, for example, hot Jupiters, which are gas giants that orbit extremely close to their stars. These planets have puzzled scientists since their discovery because their presence so close to a star contradicts standard models of planetary formation. Typically, gas giants are expected to form farther out in a star's protoplanetary disk, where conditions allow for the accumulation of gas onto a rocky core. How these colossal planets migrate inward, braving extreme heat and radiation, remains an active area of research. essential for understanding the diverse outcomes of planetary systems. Then there are terrestrial exoplanets, particularly those residing within their star's habitable zone, where conditions might be just right for liquid water to exist. While finding Earth-like planets excites the imagination, their environments can be mysterious and surprising. Some may have atmospheres dominated by thick clouds of sulfur or carbon dioxide, creating greenhouse effects that could make them much less hospitable than Earth. Additionally, planets known as super-Earths, rocky planets with masses several times that of our home planet, present another enigma. Despite their commonality, we have little understanding of their geological and atmospheric properties. Do they have plate tectonics? Could they harbor life? Each type of exoplanet, whether gas giant, ice giant, or rocky world, holds tantalizing secrets that challenge our understanding of planetary science and push the boundaries of what we know about the universe. The habitable zone, often dubbed the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface, neither too hot nor too cold. The concept is intriguing because water is considered essential for life as we know it. This zone varies depending on the star's size and temperature. For instance, the habitable zone around a small, cool red dwarf star is much closer in than that around a hot, massive star like our Sun. The existence of a planet within this zone, however, does not guarantee it will have conditions suitable for life. Atmospheric composition, geological activity, and many other factors could dramatically affect its habitability. What makes the habitable zone so mysterious is the just right balance it implies, a balance that is elusive and complex. One major uncertainty is the influence of planetary atmospheres. A thick atmosphere could trap too much heat through the greenhouse effect, making even a planet in the habitable zone stiflingly hot. Conversely, a thin atmosphere might offer little protection from cosmic radiation or fail to retain enough heat, leaving the planet cold and barren. Additionally, habitability extends beyond mere temperature. Magnetic fields are crucial to protecting the planet from a star's harmful radiation. The presence of a magnetic field can depend on the planet's internal dynamics, which are still not fully understood. Thus, while the habitable zone pinpoints a promising location for finding life-sustaining planets, it opens up a Pandora's box of questions about what combinations of conditions truly make a world habitable. The Kepler Space Telescope has revolutionized our understanding of exoplanets, revealing the astonishing diversity and sheer abundance of planets beyond our solar system. Launched in 2009, Kepler's primary mission was to survey a small patch of the Milky Way to determine how common Earth-like planets might be. Over its operational life, Kepler discovered more than 2,600 exoplanets, with thousands more potential candidates awaiting confirmation. This groundbreaking achievement has shown that planets are far more common than previously thought, with estimates suggesting that there are likely billions of planets in our galaxy alone. Kepler's discoveries have also highlighted the surprising variety of planetary systems. It found planets of all sizes, from smaller than Earth to larger than Jupiter, and in numerous configurations. Some star systems house multiple planets in tight orbits, while others feature giant planets orbiting far from their stars. Kepler has identified intriguing Earth-sized planets in the habitable zones of their stars, where conditions might be right for liquid water and potentially life. These findings have challenged and refined existing models of planet formation and migration, suggesting that our solar system's architecture, once considered the norm, may actually be just one of many possible outcomes. Through these revelations, Kepler has not only expanded the catalogue of known exoplanets, but has also deepened our understanding of the complex processes that shape planets and their environments throughout the galaxy. Among the multitude of exoplanets discovered, several have emerged as particularly promising candidates for the potential to harbour life. One of the most notable is Kepler 186f, located roughly 500 light-years away in the constellation Cygnus. Kepler 186f is an Earth-sized planet that resides within its star's habitable zone, where conditions might be right for liquid water to exist. This exoplanet orbits a cool red dwarf star, and although its atmospheric composition remains unknown, its size and location make it a compelling target for future study. Another intriguing candidate is TRAPPIST-1e, part of the remarkable TRAPPIST-1 system located about 40 light-years away in the constellation Aquarius. This system boasts 7 Earth-sized planets, 3 of which are within the habitable zone. TRAPPIST-1e stands out due to its Earth-like size, density, and the potential for a temperate climate. Its nearby distance from Earth enhances the prospects for detailed observation and analysis with upcoming telescopes. Additionally, Proxima Centauri b, orbiting the closest star to our solar system, Proxima Centauri, lies within its star's habitable zone and has garnered significant interest. Though its habitability is debated due to intense stellar flares from its host star, the planet's proximity, just over 4 light-years away, makes it an accessible and tantalizing candidate for future exploration. These exoplanets, along with others like Ross 128b and LHS 1140b, represent some of the most promising targets in the quest to find extraterrestrial life. Advances in telescope technology and techniques will soon allow astronomers to probe these worlds' atmospheres for biosignatures, potentially answering the age-old question of whether we are alone in the universe. Detecting extraterrestrial life presents a formidable array of challenges, compounded by the vastness of space and the limitations of current technology. The first major hurdle is the incredible distance involved. Even the nearest exoplanets are light-years away, making direct exploration with spacecraft largely impractical with present-day propulsion systems. Consequently, astronomers must rely on remote sensing techniques, such as analyzing the light spectra from these distant worlds to infer their atmospheric composition. However, these measurements can be exceedingly faint and often contaminated by the light from the host star, necessitating advanced telescopes with incredibly precise instrumentation and data analysis methods. Another significant challenge lies in interpreting the data collected. Biosignatures, which are indicators of potential life, can be subtle and ambiguous. For instance, oxygen is a key biosignature because it's produced in large quantities by photosynthetic life on Earth. But oxygen can also be generated through abiotic processes like photolysis, where water molecules are split by ultraviolet light. Distinguishing between biological and non-biological sources of such indicators requires a deep understanding of the planet's entire environmental context, including its geological activity and atmospheric chemistry. Moreover, life elsewhere might be fundamentally different from life on Earth, potentially relying on chemistries and processes that are not yet understood by scientists. This introduces the possibility of overlooking or misidentifying signs of extraterrestrial life because they don't conform to earthly expectations. The quest to detect extraterrestrial life is as much about overcoming technological and interpretive obstacles as it is about pushing the boundaries of our scientific understanding. The formation of our solar system is surrounded by several enduring mysteries that continue to intrigue astronomers and planetary scientists. One of the primary enigmas centers on the process of planet formation itself. The widely accepted nebula hypothesis posits that the Sun and planets formed from a cloud of gas and dust about 4.6 billion years ago. However, the details of this process remain unclear. For instance, how did the protoplanetary disk evolve to produce such a diverse set of worlds, from rocky terrestrial planets like Earth to gas giants like Jupiter and distant ice giants like Neptune? The precise mechanisms that determine the varied compositions and locations of these planets involve complex interactions of gravitational forces, collisions, and accretion processes that scientists are still working to fully understand. Another significant mystery involves the late heavy bombardment, a hypothesized period occurring about 700 million years after the solar system's formation. During this time, the inner planets, including Earth and the Moon, experienced an intense barrage of impacts from asteroids and comets. The cause of this bombardment remains a subject of debate. Some theories suggest it was triggered by the migration of the gas giants, particularly Jupiter and Saturn, whose gravitational perturbations could have destabilized the orbits of smaller bodies in the asteroid and Kuiper belts. This period may have had profound implications for the development of life on Earth, as it could have delivered water and organic compounds critical for life's emergence. Yet direct evidence for this event is sparse, primarily inferred from crater counts on the Moon and other planetary bodies. The intricacies of these ancient processes remain one of the key puzzles in planetary science, driving ongoing research and exploration missions to unlock the secrets of our cosmic origins. The formation of the Sun is rooted in the grand narrative of stellar evolution, beginning about 4.6 billion years ago in a dense region of a molecular cloud, often referred to as a stellar nursery. This process started with the gravitational collapse of a portion of the cloud, triggered perhaps by the shock wave from a nearby supernova. As the region collapsed, it spun faster and flattened into a swirling protoplanetary disk, with most of the material coalescing at the center to form a protostar. Over time, the protostar grew increasingly dense and hot until nuclear fusion ignited in its core, giving birth to our Sun. The leftover material in the disk began to clump together, eventually forming the planets, moons, and other bodies of the solar system. Despite our understanding of this broad outline, the Sun still holds many mysteries. One major enigma is the solar corona, the Sun's outermost layer, which is unexpectedly hotter than its surface. The corona reaches temperatures of over 1,000,000 degrees Celsius, while the surface, or photosphere, is only about 5,500 degrees Celsius. This counterintuitive temperature gradient baffles scientists, who are investigating mechanisms such as magnetic reconnection and wave heating as possible explanations. Another mysterious aspect is the solar magnetic cycle, an approximately 11-year cycle during which the Sun's magnetic field flips. This cycle influences solar activity, including sunspots, solar flares, and coronal mass ejections, all of which can impact space weather and Earth's own magnetic environment. Despite its regularity, the exact drivers of this cycle and the reasons for its variability from one cycle to the next are not fully understood, posing significant questions about the dynamics of magnetic fields in stellar interiors. Exploring these mysteries not only enhances our comprehension of the Sun, but also provides critical insights into the behavior of other stars across the cosmos. The planets in our solar system present a myriad of unexplained phenomena that continue to captivate scientists and fuel ongoing research. Take, for example, Jupiter's Great Red Spot, a massive storm larger than Earth that has raged for at least 400 years. Despite its longevity, the mechanisms behind its persistence and gradual shrinking over recent decades remain a puzzle. The storm's incredible stability defies typical atmospheric dynamics observed on Earth, prompting questions about the unique atmospheric chemistry and internal heat sources of Jupiter that might be contributing to this anomaly. Another unexplained phenomenon is Saturn's enigmatic hexagon at its North Pole. Discovered by the Voyager spacecraft in the early 1980s and observed in detail by the Cassini mission, this six-sided jet stream spans over 20,000 miles and exhibits a stability that is bewildering. Whereas hexagonal patterns are rare in nature, their occurrence in the turbulent atmosphere of Saturn is particularly perplexing. Scientists speculate that the hexagon could be a result of complex interactions between deeper atmospheric currents and the planet's rapid rotation, but no comprehensive model has yet fully explained this peculiar feature. Mars, our neighboring red planet, also presents perplexing mysteries, such as the recurring slope lineae, RSL. These dark streaks appear seasonally on Martian slopes and have been hypothesized to be related to flowing briny water, but the exact nature of these flows remains uncertain. Recent studies suggest that they could result from dry granular flows or subsurface ice melting under specific conditions, complicating our understanding of Martian hydrology and the potential for life. These unexplained phenomena highlight the diversity and complexity of planetary environments, encouraging continuous exploration and observation to unravel the secrets of our solar system. Dwarf planets, the smaller celestial bodies orbiting the Sun, harbor some of the most intriguing mysteries in our solar system. One of the most enigmatic is Pluto, the erstwhile ninth planet. When the New Horizons spacecraft performed its flyby in 2015, it revealed a world far more complex than anticipated. Pluto's surface features vast plains of nitrogen ice, towering mountains made of water ice, and even signs of potential cryovolcanism, volcanoes that spew icy materials instead of molten rock. One particularly perplexing feature is Sputnik Planitia, a heart-shaped basin that appears to be surprisingly young and could be the result of ongoing geological processes. This region's convection and the presence of floating icebergs suggest active geologic phenomena which challenge previous notions that such small, distant worlds would be geologically dead. Ceres, the largest object in the asteroid belt and the only dwarf planet within the inner solar system, also presents fascinating enigmas. Observations from the Dawn spacecraft revealed bright spots on its surface, primarily in the crater Ocata, which have been identified as deposits of sodium carbonate, a type of salt. These spots indicate the presence of subsurface briny water in Ceres' past, raising questions about its ability to harbor life. Furthermore, Dawn detected organic molecules on Ceres, which adds another layer of intrigue. The origin of these molecules and the processes that delivered them to Ceres remain subjects of active research. One tantalizing possibility is that they formed right on Ceres itself through processes that are still not fully understood. These dwarf planets demonstrate that even the smaller and more distant members of our solar system can possess fascinating, active, and complex histories. Their study not only enriches our understanding of planetary formation and evolution, but also fuels the search for life in unexpected places. Asteroids and comets serve as cosmic time capsules, preserving invaluable clues about the early solar system's origins and evolution. These small bodies are considered to be remnants from the solar system's formation, holding unaltered material that hasn't experienced significant processing or differentiation like the larger planets and moons. Studying them allows scientists to glimpse the primordial conditions that existed over 4.6 billion years ago when the Sun and planets were first taking shape. Asteroids, primarily found in the asteroid belt between Mars and Jupiter, provide insights into the building blocks of terrestrial planets. Their diverse compositions reflect the variety of materials present in the early solar nebula. Some, like carbonaceous chondrites, contain organic compounds and water-bearing minerals, suggesting that they may have played a vital role in delivering water and essential elements to Earth, contributing to the conditions necessary for life. Additionally, the study of asteroid collisions and their resultant fragments offers a deeper understanding of the dynamic processes that influenced planetary formation and the subsequent evolution of the solar system. Comets, originating mostly from the distant Oort cloud and Kuiper belt, carry ices and volatile compounds, including water, carbon dioxide, methane, and ammonia. These icy bodies are thought to be relics from the outer regions of the solar nebula, providing a stark contrast to the rocky makeup of asteroids. Missions like the European Space Agency's Rosetta, which studied Comet 67P/Churyumov-Gerasimenko, have revealed complex organic molecules, hinting at the potential for comets to deliver prebiotic chemistry to early Earth. The isotopic ratios of hydrogen in cometary water compared to Earth's oceans also offer clues about the contributions of these celestial wanderers to our planet's water inventory. Together, the data gleaned from asteroids and comets paints a richer, more detailed picture of the solar system's primordial environment. By unraveling the mysteries of these ancient objects, scientists can reconstruct the sequence of events that led to the formation of the planets and ultimately understand the origins of the complex and diverse solar system we observe today. Space exploration has dramatically expanded our understanding of the cosmos, uncovering mysteries that continue to reshape our perspective of the universe. One of the most groundbreaking discoveries came from the Hubble Space Telescope, which has provided us with unprecedented views of deep space. Hubble's observations have led to the identification of thousands of galaxies, some of which date back to just a few 100 million years after the Big Bang. These early galaxies offer crucial insights into the universe's infancy and the processes that governed its evolution. Furthermore, Hubble has played a key role in the discovery and study of dark energy, a mysterious force driving the accelerated expansion of the universe. This finding has fundamentally changed our grasp of the universe's structure and fate, posing new questions about the underlying nature of cosmic forces. Mars exploration missions, such as those conducted by rovers like Curiosity and Perseverance, have peeled back layers of Martian history, revealing evidence of past water flows and complex geology. These findings hint at the planet's potential to have supported microbial life in the distant past, leading to renewed interest in astrobiology and the search for biosignatures. Meanwhile, missions such as the Cassini-Huygens mission to Saturn have unveiled stunning details about the planet and its moons. Cassini's dive through the geyser plumes of Enceladus, one of Saturn's moons, revealed the presence of complex organic molecules and a subsurface ocean, suggesting that this icy moon could harbor the conditions necessary for life. In the realm of human exploration, the Apollo missions to the moon not only achieved the first manned lunar landings, but also brought back lunar rocks that have offered invaluable information about the moon's composition and history. These samples have allowed scientists to understand the moon's role in the broader context of solar system evolution, particularly in terms of solar-wind interactions and the history of meteoritic impacts. Lastly, the Voyager probes, launched in the 1970s, continue to send back data as they travel through interstellar space, providing the first direct measurements of this uncharted territory. Each of these missions and instruments, whether robotic or manned, has contributed to a profound transformation in our understanding of the universe, uncovering mysteries that challenge our scientific paradigms and inspire future generations to continue exploring the final frontier. Past space missions have yielded a wealth of knowledge, but they have also left us with significant unknowns that continue to puzzle scientists and drive future exploratory efforts. One of the most intriguing enigmas comes from the Apollo missions to the moon, which brought back rock samples rich in information but also riddled with mysteries. For instance, the moon's unexpectedly large abundance of certain isotopes, such as oxygen-17 and oxygen-18, closely match those found on Earth, hinting at a shared origin or a cataclysmic event like the giant impact hypothesis. However, this hypothesis, which suggests that the moon formed from the debris of a colossal collision between a young Earth and a Mars-sized body, still faces unresolved questions about the exact mechanics and aftermath of such an event. The Viking missions to Mars in the 1970s conducted experiments designed to detect signs of life. While the results were largely interpreted as negative, one of the experiments, the labeled release experiment, reported results that some researchers argue could be consistent with microbial metabolism. This has led to ongoing debates about whether Viking may have indeed detected Martian life, or whether the results were due to chemical reactions unrelated to biological processes. The ambiguity of these results continues to challenge scientists to develop better life detection methodologies and instruments for future missions. Another significant unknown comes from the Galileo mission to Jupiter, which provided spectacular insights into the Jovian system and its moons, but left lingering questions about Europa. Galileo revealed strong evidence for a subsurface ocean beneath Europa's icy crust, pointing to this moon as one of the most promising places to search for extraterrestrial life. However, detailed knowledge about the thickness of the ice, the composition of the ocean, and the potential for hydrothermal activity remains elusive because Galileo was not equipped with the instruments needed for these specific measurements. Returning to Saturn, the Cassini mission ended by plunging into the planet's atmosphere, effectively eliminating the possibility of future data collection from this probe. While Cassini extensively studied Saturn and its moons, including revealing geysers erupting from Enceladus's south pole, it left unanswered questions about the internal structure of Saturn, the detailed composition of its rings, and the specific mechanisms driving the moon's geological activity. Each of these missions has expanded our horizons while simultaneously sparking new questions, ensuring that the quest for understanding our solar system remains an ongoing and exciting journey. The Hubble Space Telescope has been a cornerstone of modern astronomy, uncovering numerous mysteries that have profoundly altered our understanding of the universe. One of its most compelling discoveries is the accelerated expansion of the universe, attributed to the mysterious phenomenon known as dark energy. By observing distant supernovae and measuring their brightness, Hubble provided evidence that the universe is not just expanding, but doing so at an increasing rate. This finding has introduced a fundamental mystery: the nature of dark energy and its implications for the fate of the universe. Despite numerous theories, dark energy remains one of the most significant unknowns in cosmology, challenging our comprehension of the cosmos's underlying structure and evolution. Another major enigma revealed by Hubble is the complex and varied nature of exoplanets and their atmospheres. By observing the light that filters through these distant worlds' atmospheres, Hubble has detected unexpected chemical signatures such as water vapor, methane, and even hints of potential biosignatures under certain conditions. These observations have complicated our understanding of planetary habitability and atmospheric dynamics, revealing a diversity far beyond what scientists had anticipated. For instance, the detection of water vapor in the atmosphere of the exoplanet K218b, a super-Earth located within its star's habitable zone, has opened questions about the potential for life and the geochemical processes occurring on such worlds. Additionally, Hubble has observed peculiar structures and behaviors in galaxies, such as the presence of supermassive black holes at their centers and the formation of star clusters in extreme environments. The telescope's deep-field images have exposed galaxies in various stages of evolution, some over 13 billion years old, providing a window into the early universe. These ancient galaxies often appear smaller and more irregular than modern ones, prompting questions about how they grew and evolved into the structured systems we observe today. Moreover, Hubble's detailed images of the outer planets in our own solar system have unveiled dynamic and changing environments. For instance, it captured seasonal changes on Saturn and the evolving weather patterns on Jupiter, including the dynamics of the Great Red Spot. These observations have highlighted the complexity of planetary atmospheres and climate systems, even within our solar system. All these mysteries uncovered by Hubble have not only enriched our knowledge, but have also set the stage for future explorations, urging the next generation of telescopes, like the James Webb Space Telescope, to delve deeper into these cosmic conundrums. Consider the vast expanse of space and the immense ambition of mankind to explore it. As we look toward the future, unknowns abound. One significant question mark is the long-term effects of space travel on the human body. While we know that prolonged exposure to microgravity can lead to muscle atrophy and bone density loss, scientists are still unsure about the cumulative effects of radiation from cosmic rays outside the protective bubble of Earth's magnetosphere. Studies project that astronauts on a mission to Mars, which could take up to 3 years, could receive an effective dose of radiation that significantly increases their cancer risk. This underscores the urgent need for effective shielding technology, which is currently a work in progress. Another unknown involves the sustainability and self-sufficiency of long-term missions. Future expeditions to places like Mars or beyond would necessitate growing food, recycling water, and generating oxygen, all within the confines of a spacecraft or habitat. Experiments conducted on the International Space Station have shown that growing plants in microgravity is possible, but the full scale of what's required for a sustainable supply chain remains largely theoretical. Added to this, there are technical hurdles such as resupply logistics and the development of autonomous systems that can make critical decisions independently. These unresolved challenges make it clear that the next giant leap for mankind requires not just cutting-edge technology, but also a profound increase in our understanding of life support systems in the harsh environment of space. The International Space Station, orbiting Earth at an altitude of approximately 250 miles, serves as a unique observatory and scientific laboratory that contributes profoundly to solving cosmic mysteries. On board the ISS, astronauts conduct experiments that are impossible to perform on Earth's surface due to gravity, providing insights into fundamental physics. For example, the Alpha Magnetic Spectrometer 2, AMS-02, is a particle physics experiment module mounted on the ISS that studies cosmic rays. Comprised of ultrasensitive detectors, the AMS-2 has successfully detected billions of cosmic ray events. This data is invaluable as it could potentially decode the nature of dark matter, the invisible substance making up about 85% of the universe's mass. Additionally, the ISS plays a crucial role in studying the behavior of fluids, gases, and other materials in microgravity. These investigations help refine models of stellar formations and the behavior of interstellar mediums, contributing to our comprehension of galaxy formation and star life cycles. The ISS also serves as a testbed for astrophysics and planetary science instruments. For instance, the NISA, Neutron Star Interior Composition Explorer telescope, installed on the ISS in 2017, studies neutron stars, black holes, and other cosmic phenomena using X-ray emissions. By observing these objects from the unique vantage point of space, Free from the distorting effects of the Earth's atmosphere, NICER has provided groundbreaking data on the dense matter within neutron stars, shedding light on the workings of the most extreme environments in the cosmos. Thus, through its diverse scientific endeavors, the ISS remains a cornerstone for unraveling some of the universe's most profound mysteries. Quantum mechanics, the fundamental theory in physics, reveals a realm of the universe that is both perplexing and magnificent, often defying our classical intuitions. At its heart, quantum mechanics introduces the mystery of superposition, where particles like electrons exist in multiple states simultaneously. For instance, before measurement, an electron can be thought of as being in a state where it is both here and there, challenging our classical understanding of position and momentum. This phenomenon is famously illustrated by Schrödinger's cat, a thought experiment whereby a cat in a sealed box is simultaneously both alive and dead until observed. Entanglement is another enigma illuminated by quantum mechanics. When two particles become entangled, the state of one instantly influences the state of the other, regardless of the distance separating them. Einstein famously referred to this as spooky action at a distance, as it suggests information exchange faster than the speed of light, which conflicts with the theory of relativity. Experiments have repeatedly confirmed entanglement, leading to potential applications in quantum computing and cryptography. These quantum computers could, theoretically, solve problems in seconds that would take classical computers millennia, revolutionizing fields from drug discovery to climate modeling. Moreover, quantum mechanics brings forth the notion of particle-wave duality, which posits that particles exhibit both particle and wave-like properties. This duality is evident in phenomena like the double-slit experiment, where particles such as photons create an interference pattern when not observed, but behave like particles when measured. Such revelations force us to rethink the very fabric of reality, suggesting a universe fundamentally probabilistic at its core, rather than deterministic. These mysteries not only deepen our understanding of the microscopic world, but also inspire profound philosophical questions about the nature of reality and our place within it. Quantum mechanics fundamentally challenges our classical understanding of the cosmos by introducing concepts that seem counterintuitive, yet are crucial for explaining the behavior of the universe at the smallest scales. One of the most profound challenges it introduces is the idea that the universe is fundamentally probabilistic. Unlike classical mechanics, where the future position and velocity of an object can be determined precisely if its current state is known, quantum mechanics only provides probabilities for where a particle might be found or how it might behave. This lack of determinism implies an intrinsic randomness to the fabric of reality, shaking the very foundations of classical physics and our understanding of predictability in the universe. Furthermore, quantum mechanics presents the perplexing reality that particles can be entangled over vast distances, leading to phenomena that defy classical logic, such as instantaneous communication between entangled particles, regardless of the space separating them. This spooky action at a distance, as Einstein termed it, not only challenges the speed limit imposed by the speed of light, but also forces a re-evaluation of the nature of space and time itself. The implications of quantum entanglement are particularly significant when considering theories of quantum gravity and the quest for a unified theory that bridges general relativity with quantum mechanics. Understanding how these two powerful, yet seemingly incompatible theories can coexist is one of the foremost challenges in cosmology and theoretical physics today. Additionally, the concept of wave-particle duality disrupts our classical view that particles and waves behave distinctly different. In the quantum realm, entities such as electrons and photons exhibit properties of both, depending on how they are measured. This duality is famously demonstrated in the double-slit experiment, where light and matter display characteristics of both waves and particles, leading to interference patterns when not observed, yet behaving like particles when measurements are taken. This experiment forces us to reconsider the notion of measurement and observation, pondering whether reality exists independently of our observation, or if our act of measuring the universe somehow contributes to its very existence. Thus, quantum mechanics not only challenges our classical intuition, but also opens up a realm of possibilities and questions that push the boundaries of our understanding of the cosmos. The theory of relativity, articulated through Einstein's special and general relativity, poses several profound mysteries that continue to intrigue scientists and philosophers alike. Special relativity, which deals with objects moving at constant speeds, introduces the counterintuitive reality that time and space are not absolute, but relative. As an object approaches the speed of light, time for it slows down relative to stationary observers, a phenomenon known as time dilation. This has been confirmed through experiments, such as atomic clocks on fast-moving jets running slower than identical stationary clocks. It implies that if one could travel at speeds approaching the speed of light, one could theoretically age much slower than those left behind, challenging our very understanding of time as a constant flow. General relativity extends these perplexities by describing gravity not as a force, as Newton posited, but as a curvature of spacetime caused by mass and energy. Massive objects like stars and planets warp the fabric of spacetime around them, and this curvature guides the motion of other objects, effectively what we perceive as gravity. One of the most intriguing consequences of this is the existence of black holes, regions of spacetime where the curvature becomes so extreme that not even light can escape. Inside a black hole, at the so-called singularity, the laws of physics as we know them break down. Concentrations of mass become infinitely dense, and our understanding of time and space collapses. This poses one of the biggest mysteries, reconciling general relativity with quantum mechanics to understand what happens at these extreme scales. Moreover, general relativity predicts phenomena such as gravitational waves, ripples in spacetime caused by accelerating massive objects. Only recently confirmed by the LIGO experiment in 2015, these waves open a new window into observing cosmic events, like black hole mergers, that were once purely theoretical. Another profound mystery lies in the implications of relativity on the expanding universe. Observations of distant galaxies show they are moving away from us, suggesting the universe itself is expanding. When extrapolated backwards, this leads to the Big Bang theory, raising yet another mystery. What happened at the very beginning of the universe? The theory suggests that all matter and energy were once compressed into an infinitely small point. But what caused this initial expansion and what came before it remains unknown. Through these and other phenomena, Einstein's theory of relativity not only challenges our classical concepts of time, space, and gravity, but also continually pushes the boundaries of physics, urging us to seek deeper truths about the fabric of reality and the cosmos. The theory of relativity profoundly transforms our understanding of the universe by reshaping concepts of time, space, and gravity. At the heart of Einstein's theory is the realization that space and time are interconnected into a single continuum known as space-time. This paradigm shift from viewing time and space as separate entities to seeing them as interwoven leads to phenomena that defy everyday experience. One striking impact of special relativity is the realization that the speed of light, approximately 186,000 miles per second, is the ultimate speed limit for any object with mass. This principle means that mass and energy are interchangeable, encapsulated in the iconic equations EMC squared dd, where energy equals mass multiplied by the speed of light squared. This equivalence of mass and energy impacts our understanding of how the universe functions, from the minute particles in an atom to the expansive realms of cosmology. General relativity further revolutionizes our view by portraying gravity not as a force between masses, but as the curvature of space-time caused by mass and energy. Massive objects like planets and stars warp the space-time around them, and this curvature directs the motion of other objects, essentially drawing them together in what we recognize as gravitational attraction. This understanding is pivotal for interpreting cosmic phenomena. For example, the bending of light around massive objects, known as gravitational lensing, allows astronomers to observe objects that would otherwise be hidden behind other cosmic structures. This insight also informs the prediction and observation of black holes, whose immense gravitational pull curves space-time to such an extent that not even light can escape from them. Moreover, general relativity underpins our comprehension of the universe's large-scale structure and evolution. The discovery that the universe is expanding, driven by observations from Edwin Hubble that distant galaxies are moving away from us, aligns seamlessly with the theory's predictions. This expanding universe implies that it originated from an initial high-density state, leading to the Big Bang theory. Relativity crucially helps scientists model the universe's past, present, and future, including phenomena like the cosmic microwave background radiation, which offers a snapshot of the early universe. Relativity compels us to rethink our perception of reality and provides the mathematical framework to explore concepts like time dilation, gravitational waves, and the curvature of space-time. It pushes the frontiers of our knowledge, allowing us to delve deeper into the nature of the cosmos and our place within it. Wormholes, speculative bridges between two distant points in space-time, are one of the most tantalizing predictions arising from the theory of general relativity. The concept of a wormhole, also known as an Einstein-Rosen bridge, posits that massive gravitational fields could warp space-time to such an extent that shortcuts between widely separated regions of the universe emerge. Imagine folding a piece of paper in half and piercing a hole through it. The two separate points on the paper, vast distances apart when flat, now connect instantly through the hole. This analogy helps us understand the essence of a wormhole, a theoretical tunnel that could connect disparate regions of space-time, potentially allowing for faster-than-light travel without violating the speed limit set by the speed of light. One of the major mysteries posed by wormholes is their stability. Current theories suggest that wormholes would require exotic matter with negative energy density to remain open and traversable. Such exotic matter would counteract the tendency of the wormhole to collapse under its own gravitational pull. However, the existence of this type of matter is purely hypothetical, and no empirical evidence has been found to date. Additionally, even if such exotic matter could be found, the quantum effects predicted by quantum field theory might still lead to the wormhole closing too quickly for anything to pass through it. Another mystery involves the potential paradoxes and contradictions related to causality and time travel. If wormholes allow for shortcuts through space-time, they could theoretically enable travel backward in time, which invites perplexing scenarios such as the grandfather paradox, where a traveler to the past could potentially prevent their own existence by altering historical events. Physicists and cosmologists grapple with these paradoxes by exploring whether the laws of nature might inherently prohibit such time travel, or if there are self-consistency principles, like Novikov's self-consistency conjecture, ensuring that any actions taken by a time traveler were always part of history. Moreover, the presence of wormholes could fundamentally alter our understanding of the universe's topology. If wormholes do exist, they may connect not just distant regions of our universe, but also entirely different universes, providing a means of multiverse traversal. This raises profound questions about the nature of reality, the structure of the cosmos, and whether our universe is but one of many in a larger multiverse. Wormholes remain speculative and enveloped in mystery. They prompt profound questions about the fabric of space-time, the nature of exotic matter, and the very principles governing causality and reality, making them one of the most exciting and enigmatic concepts in modern theoretical physics. The multiverse theory, which posits the existence of multiple, perhaps infinite universes beyond our own, represents one of the most fascinating and controversial frontiers in contemporary science and cosmology. According to this theory, these parallel universes, sometimes referred to as alternate realities or parallel worlds, could exist in different dimensions or vibrations, each with its own distinct set of physical laws, constants, and potentially even different manifestations of life. The idea of a multiverse stems from several scientific hypotheses and discoveries, including the inflationary model of the cosmos, quantum mechanics, and string theory. One of the most compelling branches of multiverse theory arises from cosmic inflation, a rapid exponential expansion that occurred fractions of a second after the Big Bang. This theory, proposed by physicist Alan Guth, suggests that our observable universe is just one bubble among countless others formed during this inflationary period. Each bubble could constitute a separate universe with its own properties. In quantum mechanics, the many worlds interpretation posits that every quantum event spawns a new, branching universe, leading to a potentially infinite number of parallel outcomes. String theory, which aims to reconcile quantum mechanics with general relativity, also implies the possibility of multiple dimensions and universes through its complex theoretical framework. Despite its allure, the multiverse theory is fraught with profound unknowns and challenges. One of the most significant issues is the question of testability and empirical evidence. Unlike other scientific theories that can be tested and verified through observation and experimentation, the multiverse hypothesis currently lies beyond our observational reach. Each separate universe, if it exists, would be isolated from our own, making direct evidence extremely difficult, if not impossible, to obtain. This lack of empirical verification raises questions about whether the multiverse can ever be more than a speculative idea. Moreover, the multiverse theory poses philosophical dilemmas and revisits fundamental questions about the nature of reality and our place within it. If there are indeed an infinite number of universes, each with its own set of physical laws, constants, and properties, what does this imply about the uniqueness or randomness of our own universe? Why do the physical constants in our universe seem finely tuned to support life as we know it? This leads to the anthropic principle, which suggests that we observe a universe capable of supporting life simply because we are here to observe it, a reasoning that some argue is circular and unsatisfying. Another critical unknown is the mechanics of how these universes interact, if at all. Would the notion of a multiverse entail occasional leaking or interaction between universes, or are they entirely isolated? These questions delve into deep theoretical territory, challenging our understanding of space, time, and the fundamental nature of existence. While the multiverse theory expands our intellectual horizons and offers intriguing possibilities about the nature of reality, it remains steeped in significant unknowns and challenges that continue to spark debate and inspire theoretical exploration among scientists and philosophers alike. String theory and its more comprehensive extension, M theory, offer revolutionary frameworks for explaining the universe's mysteries by proposing that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings. These strings can vibrate at different frequencies, with each vibrational mode corresponding to a different particle. For example, an electron would be one type of string vibration, while a quark would be another. This elegant proposal offers a unified way to describe all known particles and forces, potentially leading to the elusive theory of everything that could reconcile quantum mechanics and general relativity. String theory introduces the concept of extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. Specifically, the most studied version, known as type WTA string theory, requires 10 dimensions to be mathematically consistent. These extra dimensions are compactified, meaning they are curled up in shapes so small that they are imperceptible to current experimental tools. The shapes and sizes of these extra dimensions can influence the physical properties observed in our 4-dimensional universe, including the types of particles and forces that manifest. This idea could provide crucial insights into why the physical constants in our universe have the values they do, shedding light on what appears to be an extraordinary fine-tuning conducive to life. M theory, proposed as an overarching framework that encompasses various string theories, posits 11 dimensions and includes not only strings but also higher dimensional objects called brains. In M theory, our universe could be a 3-dimensional brain embedded in a higher dimensional space, possibly interacting with other brains. This brain-world perspective could offer explanations for phenomena such as gravity being relatively weak compared to other fundamental forces. If gravity propagates through these higher dimensions, while other forces are confined to our 3-dimensional brain, it would naturally explain its apparent weakness. One of the central mysteries tackled by string theory and M theory is the nature of black holes and the singularities within them. String theory has provided significant insights into the entropy and temperature of black holes, correlating with the work by Stephen Hawking on black hole radiation. These theories suggest that the singularities predicted by general relativity, points of infinite density where the laws of physics break down, might be smoothed out by the principles of string theory, offering a more comprehensive description of the universe's fundamental nature. However, despite these promising insights, significant unknowns remain. One major challenge is the lack of experimental evidence. The energy scales at which string theory's predictions become observable are currently far beyond the reach of our most powerful particle accelerators. Additionally, the landscape of possible solutions within string theory is vast, with an enormous number of potential compactifications and configurations of extra dimensions. Determining which, if any, corresponds to our observed universe is an ongoing challenge that requires not just advanced mathematical techniques, but also new, innovative experimental approaches. Moreover, while M-theory promises to unify the 5 different string theories into a single, coherent framework, its full formulation remains incomplete, leading researchers to continue exploring and refining its principles. String theory and M-theory propose groundbreaking ways to explain the universe's deepest mysteries by fundamentally altering our understanding of particles, forces, and dimensions. They offer potential solutions to long-standing puzzles in physics, but also open up a host of new questions and challenges that spur ongoing research and debate in the quest to understand the cosmos. The Great Attractor is one of the most enigmatic phenomena in modern astrophysics, located roughly between 150 and 250 million light-years away from Earth in the direction of the Centaurus and Hydra constellations. It is a gravitational anomaly in the intergalactic space that appears to be drawing galaxies, including our own Milky Way, the Andromeda Galaxy, and thousands of others, toward it with immense gravitational force. This colossal movement of galaxies is part of what scientists refer to as bulk flow, involving a significant portion of the observable universe heading in the same direction, influenced by the gravitational pull of the Great Attractor. What makes the Great Attractor particularly mysterious is that it lies within the zone of avoidance, a region of the sky obscured by the Milky Way's dense galactic plane filled with stars, dust, and gas that hinder direct optical observation. Despite the use of advanced technology like X-ray astronomy and radio wave observations, our view of the area is still largely obstructed, making it difficult to pinpoint exactly what constitutes this massive gravitational force. Some astronomers hypothesize that the Great Attractor is an extraordinarily dense region, possibly containing a supercluster of galaxies or an unseen mass distribution that bends the paths of galaxies through its gravitational influence. Adding to the mystery, the Great Attractor's scale and the dynamics of its gravitational influence suggest the possible existence of even larger structures in the universe, such as the Shapley supercluster, which could also be pulling on galaxies within our local universe. This hierarchical structure of cosmic attractors indicates that our universe's large-scale structure is more complex than previously thought, with multiple layers of gravitational influence exerted by vast cosmic entities that are still poorly understood. Moreover, understanding the Great Attractor can yield insights into the distribution of dark matter, which makes up about 85% of the universe's mass, but remains invisible and detectable only through its gravitational effects. If the Great Attractor comprises a significant amount of dark matter, studying it could indirectly reveal crucial aspects of this elusive substance and its role in cosmic evolution. The Great Attractor continues to be a source of fascination and perplexity for astronomers as they strive to peel back the layers of the universe's hidden structure. Its enigmatic gravitational pull, coupled with the challenges of observing it directly, keeps it at the forefront of cosmological research, driving scientific inquiry into the fundamental nature of cosmic attractors and the unseen components of the universe. Fast radio bursts, FRBs, are one of the most puzzling and intriguing phenomena in astrophysics, consisting of extremely brief but highly energetic bursts of radio waves that originate from far beyond our galaxy. Typically lasting only a few milliseconds, these bursts release more energy in that fraction of a second than the Sun emits in an entire day. Since their discovery in 2007, over 1,000 FRBs have been observed, yet their exact origins and mechanisms remain deeply mysterious. One of the key mysteries surrounding FRBs is their source. While some FRBs appear to be one-off events, others have been observed to repeat, originating from the same location in space. This distinction suggests a variety of potential sources, each presenting different astrophysical challenges. Non-repeating FRBs could be caused by cataclysmic events such as supernova or the merging of neutron stars, which would release a single burst of energy. On the other hand, repeating FRBs indicate a more stable, ongoing process. Some hypotheses propose highly magnetized neutron stars, magnetars, as potential sources, given their extreme magnetic fields and potential for high-energy emissions. Another puzzle is the distribution of FRBs. They are observed scattered across the sky without any clear pattern suggesting they come from various distant galaxies. The immense energy required for these radio bursts to be detectable over such vast distances adds to the enigma. Also confounding researchers is the fact that FRBs travel through the cosmos and interact with intervening matter, which can provide clues but also complicate their detection and analysis. The way these bursts get dispersed, frequencies arriving at Earth at different times, allows scientists to estimate their travel distance, yet tracing them back to their exact point of origin remains a formidable task. Compounding these mysteries are the unusual characteristics of some FRBs, such as polarization and changes in brightness. Some bursts exhibit extreme variations in polarization, indicating they have passed through highly magnetized regions, which might be near a supermassive black hole or within a magnetar's vicinity. Additionally, the sheer diversity in FRB's properties, from their frequency spectrum to their duration and intensity, implies multiple origins and mechanisms at play, which complicates any unified theoretical framework. Moreover, the potential implications of understanding FRBs are profound. If they can be systematically observed and traced, they could serve as cosmic probes, helping to map the distribution of matter in the universe and improve our understanding of cosmic structures and evolution. Some theories even suggest that FRBs could be signals from advanced extraterrestrial civilizations, although this remains speculative and controversial. Fast radio bursts continue to puzzle scientists due to their unknown origins, diverse properties, and the immense distances they travel. As research and technology advance, each new discovery about FRBs brings additional layers of intrigue, driving a deeper quest to understand these fleeting but powerful cosmic phenomena. The WOW signal is one of the most famous and enigmatic signals ever detected in the search for extraterrestrial intelligence. It was discovered on August 15, 1977, by astronomer Jerry R. Amon while working on a SETI, Search for Extraterrestrial Intelligence project at Ohio State University's Big Ear Radio Telescope. The signal lasted for 72 seconds, the maximum duration that the Big Ear could observe it before losing track due to the Earth's rotation. What made the signal so remarkable was its intensity and narrow bandwidth, both of which are characteristics of a transmission likely to be artificial in origin. Amon, astonished by the strength of the signal, circled it on the computer printout and wrote "WOW" in the margin, hence the name. The significance of the WOW signal lies in its potential implications. If it were indeed a transmission from an intelligent extraterrestrial civilization, it would represent the first contact humanity has ever made with an alien species. The signal's frequency, around 1420 MHz, aligns with a natural emission line of hydrogen, the most abundant element in the universe. This frequency has been considered a prime candidate for interstellar communication because hydrogen's presence is universal, making it a logical choice for civilizations looking to make contact. This bolstered the argument that the WOW signal could be a deliberate transmission rather than a random cosmic noise or human-made interference. Despite extensive follow-up observations, the exact source of the WOW signal has never been identified, adding to its mystery. Multiple attempts to detect a repeat of the signal have failed, leading scientists to consider a range of possibilities, from Earth-bound interference to a momentary alignment with an unknown extraterrestrial transmitter. The absence of a repeat occurrence complicates efforts to definitively categorize the signal, and while various hypotheses have been proposed, including reflections off space debris, the true origin remains unknown. The WOW signal holds enduring significance not only for its potential origin, but also for its impact on the field of SETI. It serves as a milestone demonstrating the feasibility of detecting potential extraterrestrial signals and inspiring further scientific inquiry. It underscores the importance of continuous and varied monitoring of the sky, utilizing different technologies and methodologies to capture fleeting or rare signals that might otherwise be missed. The WOW signal remains one of the most compelling pieces of evidence in the search for extraterrestrial intelligence, embodying both the promise and the enormous challenges of this quest. It beckons us to continue exploring the cosmos with an open mind and advanced technologies, perpetuating the hope that one day we may solve this intriguing mystery. The Pioneer anomaly refers to the unexpected deviations in the trajectories of the Pioneer 10 and Pioneer 11 spacecraft, observed after they passed beyond the orbit of Saturn. Launched by NASA in the early 1970s, these spacecraft were among the first to venture into the outer solar system, carrying instruments designed to explore the more distant planets. However, during their extended missions, scientists noticed something peculiar. Both spacecraft were experiencing a small but consistent acceleration towards the Sun that couldn't be accounted for by known physical forces or gravitational effects from celestial bodies. This anomaly was detected through precise tracking data, which revealed that the spacecraft was slowing down slightly faster than expected. The deviation was tiny, amounting to about 8.74 × 10 circumflex, 10 meters per second squared, but it persisted over time and distance, challenging scientists to identify its cause. Initial theories ranged from unexpected influences like the pressure of solar radiation and heat emissions from the spacecraft's power sources to more exotic possibilities, such as modifications to Newtonian gravity or the influence of dark matter. Despite extensive analysis, the Pioneer anomaly remained unexplained for many years, leading to a wide range of hypotheses. One of the more conventional explanations suggested that heat emitted by the spacecraft's onboard systems, including their radioactive power sources, might be creating a recoil effect that subtly altered their trajectories. This effect, known as thermal recoil force, stems from anisotropic radiation, where heat is emitted in a directionally uneven manner due to the spacecraft's design and configuration. However, modeling these thermal emissions accurately enough to reconcile the observed anomaly proved challenging. More radical speculative theories suggested that the anomaly could point to new physics, such as a need to revise our current understanding of gravity or the presence of unknown interstellar forces. These ideas sparked considerable debate, as verifying them would require observations beyond the realm of the Pioneer spacecraft alone. In recent years, more sophisticated thermal models and analyses have increasingly supported the thermal recoil hypothesis, suggesting that the heat emissions from Pioneer 10 and the 11th of May indeed account for the discrepancies. Nevertheless, while this explanation has gained significant traction, it doesn't entirely eliminate the intrigue the anomaly generated. The Pioneer anomaly serves as a reminder of the limits of our current understanding and the continual need for innovation and precision in scientific inquiry. The Pioneer anomaly stands as a compelling case study in the history of space exploration, highlighting the complexities of long-term space navigation and the ever-present potential for new discoveries that challenge our established scientific paradigms. Whether fully explained by conventional physics or hinting at new realms of understanding, the Pioneer anomaly underscores the importance of vigilant observation and open-mindedness in scientific exploration. The Kuiper Cliff refers to a sudden and unexpected drop in the number of objects beyond a certain distance in the Kuiper belt, a region of the solar system that extends from about 30 to 55 astronomical units AU from the Sun. The Kuiper belt is similar to the asteroid belt but far larger and more massive, containing remnants from the early solar system, including dwarf planets like Pluto and countless smaller icy bodies. Astronomers expected the density of these objects to gradually decline as they moved further from the Sun. However, observations revealed a dramatic and unanticipated drop-off in the number of objects beyond approximately 50 AU, which has been termed the Kuiper Cliff. This sharp decline challenges existing models of solar system formation and raises several questions about the processes that could have led to such a feature. One speculative explanation for the Kuiper Cliff involves the gravitational influence of a yet undiscovered large object, often referred to as Planet 9. This hypothetical planet, which could be several times the mass of Earth and located far beyond Neptune, might exert enough gravitational force to clear out or scatter smaller objects in its vicinity, leading to the observed drop-off. However, despite significant efforts, No direct evidence for such a planet has been found, making this hypothesis still highly speculative. Another possibility is that the current models of the solar system's formation and early evolution might be incomplete or require revision. The processes that governed the primordial solar nebula and the migration of giant planets like Jupiter and Saturn could have had more complex effects on the distribution of Kuiper Belt objects, KBOs, than previously thought. For instance, interactions with the giant planets or the gravitational perturbations from passing stars early in the solar system's history might have influenced the current structure of the Kuiper Belt in ways that aren't fully understood. Moreover, the Kuiper Cliff raises questions about the distribution and size of other KBOs further out in the solar system. If similar drop-offs or gaps exist beyond this region, they could provide additional clues about the dynamics and history of the outer solar system. Some researchers have proposed that more observational data, particularly from telescopes capable of detecting faint, distant objects, could help address these questions and refine our understanding of the Kuiper Belt's structure. The Kuiper Cliff remains a mystery because it defies current expectations and models of the solar system's formation and evolution. Its existence hints at unknown gravitational influences or dynamic processes that shaped the outer regions of our solar system. Resolving this mystery requires further observational evidence and theoretical work, making it a significant focus for astronomers interested in the hidden architecture of our cosmic neighborhood. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, as predicted by Albert Einstein's theory of general relativity in 1915. These waves travel at the speed of light, carrying information about the cataclysmic events that generated them. They were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, a monumental discovery that opened an entirely new way of observing and understanding the universe. Gravitational waves are generated by some of the most violent processes in the cosmos, such as the collision and merger of black holes, the inspiral of neutron stars, and the asymmetric supernova explosions of massive stars. When these events occur, they create distortions in spacetime that propagate outward, much like waves created by a stone thrown into a pond. The detection of these waves enables astronomers to study phenomena that are otherwise invisible or difficult to observe using conventional electromagnetic waves, such as light or radio waves. One of the profound mysteries revealed by gravitational waves is the nature of black holes and neutron stars. These detections allow scientists to measure the masses and spins of black holes with unprecedented precision. We've begun to uncover black holes that were previously unknown, including unexpectedly massive ones that challenge existing models of stellar evolution. Additionally, the merger of neutron stars, observed both through gravitational waves and electromagnetic radiation, offers insights into the behavior of matter under extreme conditions and the origins of heavy elements like gold and platinum in the universe. Gravitational waves also provide crucial data for testing the boundaries of general relativity. By precisely measuring the waveforms of gravitational waves generated by cataclysmic events, scientists can check for deviations from the predictions made by Einstein's theory. So far, general relativity has stood up to these tests remarkably well, but ongoing and future observations may reveal discrepancies that could point to new physics, potentially expanding our understanding of gravity. Moreover, there's the tantalizing possibility of detecting gravitational waves from the early universe, which could serve as a direct probe into the conditions present moments after the Big Bang. These primordial gravitational waves could reveal information about the universe's rapid inflationary phase, providing clues about its fundamental nature and origins in a way that electromagnetic observations cannot. Despite the advances in detecting gravitational waves, many mysteries remain. The sources for many of the detected waves have been identified, but there are signals with unknown origins. Some could be from exotic sources like boson stars, cosmic strings, or other phenomena not yet fully understood. Furthermore, improving the sensitivity of detectors like LIGO and its European counterpart Virgo, along with future detectors such as LISA, Laser Interferometer Space Antenna, promises to reveal even more about the dynamic universe. Gravitational waves have not only confirmed a fundamental aspect of general relativity, but have also opened up an entirely new realm of observational astronomy. They allow us to listen to the universe and uncover secrets about its most extreme and enigmatic phenomena, offering answers to long-standing questions while posing new ones that will drive scientific exploration in the decades to come. Imagine a ripple spreading across a calm pond. That's essentially what gravitational waves are, ripples in the fabric of space-time caused by the most cataclysmic events in the universe. We detect these elusive waves with incredibly sensitive instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and its European counterpart Virgo. These observatories use large L-shaped arms, each spanning up to 2.5 miles. When a gravitational wave passes through Earth, it slightly stretches and compresses these arms by less than 1,000th of the diameter of a proton. Yet, even such infinitesimal changes are enough for the laser beams bouncing between mirrors to detect. This sensitivity is nothing short of awe-inspiring and underscores the monumental precision of modern scientific instrumentation. Despite our progress, gravitational waves still present a host of tantalizing unknowns. For one, while we can trace these waves back to massive events like the collision of black holes or neutron stars, deciphering the exact nature of the sources remains a puzzle. There's an entire spectrum of gravitational waves we have yet to fully explore, like those originating from the Big Bang itself, potentially carrying imprints of the universe's infancy. Moreover, these waves could offer new clues about the mysterious dark matter, which makes up about 85% of the universe's mass, but remains invisible and enigmatic. As we continue to refine our detection methods, gravitational waves may very well open doors to entirely new fields of physics, reshaping our understanding of space, time, and gravity. Quantum entanglement is one of the most perplexing phenomena in the realm of quantum mechanics, earning a reputation for its almost magical properties. When two particles become entangled, their quantum states become intertwined in such a way that the state of one particle instantaneously influences the state of the other, even if they are separated by vast distances. Think light years apart. This isn't just science fiction. It's been rigorously tested and observed in various experiments. Consider two entangled photons. If one is found to have a particular polarization, the other's polarization is immediately known, no matter how far it has traveled from its twin. This has profound implications, hinting at a deep and not yet fully understood connectivity in the universe. The mystery of quantum entanglement lies in its defiance of classical intuition and the tenets of locality, which state that an object should only be directly influenced by its immediate surroundings. Albert Einstein famously referred to this phenomenon as spooky action at a distance, expressing his discomfort with the idea that particles could affect each other faster than light could travel between them, apparently violating the cosmic speed limit set by his theory of relativity. While the mathematical framework of quantum mechanics robustly supports entanglement, the underlying mechanisms remain an enigma. This has spurred on numerous theoretical debates and experimental ventures, driving us closer to technologies like quantum computing and quantum encryption. Entanglement not only challenges our understanding of space and time, but beckons us to reconsider the very nature of reality itself. The realm of cosmology is vast and full of captivating mysteries that continue to baffle and intrigue scientists. Among the most pressing unanswered questions is the true nature of dark matter and dark energy. Dark matter, which makes up about 27% of the universe, exerts gravitational forces yet remains invisible and doesn't interact with light. Dark energy is even more elusive, constituting approximately 68% of the universe and driving its accelerated expansion. Detecting these enigmatic substances requires innovation and perhaps a profound shift in our understanding of fundamental physics. Are they new, undiscovered particles, or do they hint at modifications to our existing theories of gravity? This remains one of the biggest puzzles for cosmologists. Another major enigma is the origin and fate of the universe. While the Big Bang theory describes how the universe expanded from an extremely hot and dense state, it leaves the question of what preceded it unanswered. Additionally, the ultimate fate of the universe, whether it will continue to expand indefinitely, collapse back into a big crunch, or undergo a big freeze or a big rip, depends on currently unknown properties of dark energy and the universe's overall geometry. Moreover, the universe's asymmetry, where we see more matter than antimatter, presents yet another conundrum. The laws of physics symmetrically produce both matter and antimatter, so why does the cosmos lean heavily towards matter? Answering these grand questions poses significant challenges, but promises revolutionary advances in our understanding of existence itself. Cosmic voids are vast, empty regions of space that can span tens to hundreds of millions of light years, devoid of galaxies, stars, and most forms of matter. These enormous gaps present a paradox of emptiness in a predominantly matter-filled universe, challenging our understanding of cosmological structure and evolution. Traditional models of the universe are based on the notion that matter clumps together due to gravitational forces, leading to the formation of galaxies, clusters, and large-scale structures. However, the existence of these immense voids forces us to re-examine how matter distributes and interacts on the grandest scales. Despite their name, cosmic voids are not completely empty. They contain dark matter and sparse hydrogen gas, but the mechanisms driving the formation and expansion of these vast empty spaces remain a subject of intense study. The study of cosmic voids also tests the current cosmological theories, particularly the lambda cold dark matter (LCDM) model, which combines dark matter and dark energy to explain the universe's evolution. Voids provide a natural laboratory to explore these elements and test the predictions of the LCDM model. They act as a contrasting window to dense regions, allowing scientists to study the influence of dark energy on cosmic scales more directly. Differences between observations and theoretical predictions within these voids could hint at new physics or modifications to our understanding of gravity and dark energy. Such discrepancies can drive groundbreaking advancements, revealing that perhaps our current theories, though successful elsewhere, are incomplete. By unraveling the mysteries of cosmic voids, we edge closer to a more comprehensive understanding of the universe's nature, formation, and ultimate fate. High-energy cosmic rays are another perplexing phenomenon in the cosmos, representing particles that travel through space at near-light speeds. Detected when they strike the Earth's atmosphere, these particles, often protons or atomic nuclei, collide with molecules in the air, creating showers of secondary particles observable with ground-based detectors. The origins of these cosmic rays remain one of the top enigmas in astrophysics. While lower-energy cosmic rays are typically linked to solar flares or supernova remnants, high-energy cosmic rays with energies exceeding 10 circumflex 19 electron volts pose a considerable mystery. Potential sources include extremely energetic events, such as active galactic nuclei, gamma-ray bursts, or even more exotic phenomena like the decay of hypothetical super-heavy particles from the early universe. Another enigma surrounding high-energy cosmic rays is their journey through space, particularly how they manage to retain such high kinetic energies over immense distances. As they travel, these particles encounter interstellar magnetic fields that can alter their directions, making it challenging to trace them back to their origins. Additionally, their interactions with cosmic microwave background radiation can lead to energy loss, further complicating our understanding of their propagation and distribution. This phenomenon, known as the Greisen-Zatsepin-Kuzmin (GZK) cutoff, suggests there is a theoretical limit to the energy of cosmic rays that remain after traversing the vast expanse of the universe. By studying high-energy cosmic rays, scientists hope to unlock new insights into both their origin and the fundamental processes governing high-energy particle physics, possibly revealing new phenomena and forces that shape our universe on the grandest of scales. The depths of space are a frontier full of unknown phenomena, where our current scientific instruments and theories can only glimpse hints of what might exist. One tantalizing possibility involves the existence of exotic objects, such as primordial black holes. Unlike standard black holes formed from collapsing stars, primordial black holes could have formed soon after the Big Bang from dense fluctuations in the early universe. These black holes could range from minuscule subatomic sizes to massive ones weighing more than 1,000 suns. Detecting them could offer valuable insights into the mysterious dark matter, as they might constitute a significant portion of this elusive mass in the universe. Moreover, there are theoretical constructs like wormholes, which are shortcuts through spacetime, hypothesized by solutions to Einstein's field equations. If wormholes exist, they could connect distant regions of space and time, potentially allowing for faster-than-light travel and new methods of cosmic exploration. However, the the stability and traversability of such structures remain deeply theoretical and unproven. Similarly, the concept of parallel universes or a multiverse introduces the possibility that our universe is just one of many, each with different physical constants and laws. This idea, though radical, stems from interpretations of quantum mechanics and string theory, suggesting a reality far more complex and varied than we perceive. Unknown forms of energy and matter, entirely different from the particles and forces we know, might also inhabit the universe's vast expanses. These could include new types of neutrinos, undiscovered particles predicted by extensions of the standard model of particle physics, or entirely new states of matter. The discovery of such phenomena would not only revolutionize our understanding of physics, but might also explain long-standing cosmic mysteries, from the nature of dark energy driving the universe's accelerated expansion to the fine-tuning of fundamental constants that allow life to exist.